And that's where this screen grab is from. But basically, ONNX was designed to solve a number of machine learning problems that different companies were having. We were having it at Microsoft, and then when we talked to folks in the industry, they were all having similar problems as well. And at the core of it, it's about interoperability in multiple dimensions. So when you boil it down, ONNX really kind of consists of two key things. There's a common set of operators that define the building blocks for machine learning models. And then there's a common file format for exchanging these models between different components, like the training systems and the inferencing systems. And this was super useful for a lot of different people, and for a couple of reasons. One, if you're on the software side, you're creating applications and services and ML models, then ONNX lets you kind of use whichever framework or tool you want. You'll hear about all the different frameworks that support ONNX later today, and kind of get this common model that can run on a variety of different hardware. So you have access to multiple frameworks, and you have access to multiple types of hardware and hardware accelerators. On the flip side, if you're a hardware vendor, then ONNX kind of gives you access to customers who are using all these various frameworks. Like, you don't have to spend a bunch of time customizing for each specific framework out there, because there's a few head ones, but then it's like a long tail of different tools and frameworks that create these models. And so ONNX helps you kind of reach all of those customers a little bit more easily. So, okay, thank you. ONNX has been pretty useful. So there's a lot of people in the community who are using it. These are just some of the logos of the companies that are using it. And it's great to see this awesome community that has evolved around ONNX over the past few years. By the way, if your logo is not on here and you want it to be, please reach out and we'll get that taken care of. And ONNX, there's a community around ONNX, but the ONNX development is also done by the community. ONNX is an open source project. It's part of the Linux LF AI and Data Foundation, the Linux Foundation. And it has open governance. That means there's no one company that controls it, right? And this comes out in kind of two ways. One, there's a steering committee that's elected every year. We actually just finished the elections a few weeks ago, and there was a blog that went out earlier this week announcing the results of that. So I'm really happy to welcome, can you go back? There we go. I'm really happy to welcome Andreas Fellner. So he's a new member on the steering committee. And I want to thank Wenming, who's in the audience, who was on the steering committee last year for his service for all the last whole year. So while there's a steering committee that kind of looks over broad things for the project, the real work for ONNX actually happens in the special interest groups and the working groups. This is where all the work, the actual technical work, gets done. And we have a number of SIGs, as we call them, and working groups here. There's architecture and infra, operators, converters, the models and tutorials, and then there's a new pre-processing working group that's happening as well. And these are led by community members as well. And we've had some new leaders join us in this past 9 months or so. So, the ones with the stars, Lakun, Thiago, Kevin, Jackie, thank you for stepping up and helping lead these SIGs and working groups. And of course, thank you to the folks who have been already leading the working groups for some time. And you're going to hear from each of these working groups on what they've been doing over the last few months and the latest technical updates. But for now, I'm going to hand it off to Mayank, who's going to give you an update on the latest progress with ONNX.
Thanks, Prashant. Good morning, everyone. I'm Mayank. I work for NVIDIA in the TensorRT group, and I'm on the steering committee. So I'm going to be presenting a few slides on the state of the union for ONNX. Next slide, please. So this chart shows some companies that contribute tools to different categories of ONNX. We've divided this into 3 categories, and we couldn't fit everyone in there, so apologies if we left anyone out. But the 3 categories, we defined 3 categories. The first one is tools that help in the creation of ONNX models or manipulation of existing ONNX models. Obviously, all the major frameworks show up there, and then there are some tools that that allow you to modify existing ONNX models to add, remove nodes, etc. The next section, the next category is tools that are used for running these ONNX models or compiling them to optimize. ONNX Runtime obviously is very well known, supports several device backends, and then a lot of companies produce tools that support their particular architectures. And the last one, the last category is tools used for visualization of ONNX models. And Netron is familiar to most people, but there are other options as well. Next slide. Okay, now I'm going to talk about some statistics from engagement, about engagement and usage of ONNX. These are over the last 6 months since the last community update was made. We see good metrics across the board. The number of PRs has gone up by 15%, 10% more contributors, 10% more stars, 63% more dependent repos, 28% more forks, 68% more mentions in research papers, which is great. The number of models in the model zoo has gone up by 50%, over 50%, which is awesome, and a very healthy increase in the number of monthly downloads. So these stats are quite encouraging to see. Next slide. Okay, so now I'll talk quickly about the few releases that have happened since the last community update. ONNX 1.11 was released earlier in February this year. That came with Opset 16, which introduced a few new operators and updated some operators. The ONNX Model Hub was introduced, which is a tool that lets you pull pre-trained models from any model zoo, basically, but the ONNX Model Zoo by default, and you can point it to a different model zoo that follows the prescribed structure. There were a few utilities, other utilities introduced as well. The Compose utility allows folks to create combined models with pre-processing graphs and the pre-processing networks and inference networks. There was a function builder utility introduced that helps creating function ops. There were bug fixes, infra improvements, and doc updates. If you go to the release page by following the link here, that will give you all details of which ops were introduced, and it will also let you find out more about these utilities if you're interested. Next slide. And then a few days ago, ONNX 1.12 was introduced as well. That came with ONNX Opset 17 with a lot more new operators and a few updated operators as well. There were shape inference enhancements, bug fix, infra updates, and doc updates. We dropped support for Python 3.6 and added support for Python 3.10. And we also dropped support for 32-bit Linux due to low usage. And again, this link will lead you to the release notes for this release with more details. And a big thank you to everyone in the community for countless hours of work that helped make all these releases happen. That's it for this slide. And now I'll turn it over to Rajiv, who will guide you through the roadmap process.
Thank you, Mayank. So I'll cover the ONNX roadmap process and the different updates and the status that have happened to some of the submissions from the community. So we held like a full-fledged request for the features by requesting the community to submit what they would like to see. And these are long-term intercepts, right? And some are ongoing, some are finished. So you'll see in the status that I'll go through. So the request for features happened in July 2021 of last year. And then there were different presenters with selected topics. So we had a very good 6 weekly community roadmap discussions. And after the discussion, we had to go through and refer the submitters to the different SIGs and working groups for the ongoing discussion and the implementation as well. So that process completed in October 2021. So it's been about close to 6 months, essentially. And there were 12 roadmap requests that were selected for further progress and assigned to the SIGs and the working groups. So basically, these are long-term intercepts, right? And you will see in the status that I will go through. Next slide. So this is a quick snapshot of what those requests were. For example, I'll not go in detail, to each one of them, but new operators for data pre-processing. There is a pre-processing working group, and that is being handled in that particular working group. So essentially, there were different operators that were needed, and these are also going over to the operator SIG for approval. So a lot of them got implemented, and still the work continues on the further updates, like, for example, processing the dates and so on. And the next two were more of a request to have a C API. Today, it's Python wrapper over C++. So there was a request coming in from Oracle that they wanted a C API for ONNX. And currently, Java and C have their own, C# have their own kind of wrapper and implementation for the two projects. And there is currently like Java framework, which Oracle has already open sourced. And this work continues, and probably it will need to be assessed. Like, there is more structured, quantized information that is needed to flow through the model and the tensors, and that is also trying to get a path identified of how that can be done. And on the end-to-end pipeline with ONNX operators, this is identified as a long-term intercept, and further refining of the proposal is happening at this moment. And you can see like the proposed SIGs that the requesters have been asked to go and work with. So if in the SIG as chairs, if you see some of these come as requests, these are sort of being identified as long-term, not essentially like as is accepted, but going through the regular cycle of understanding and what needs to be done. For the converters, there is some progress. Some of the higher functioning ops have gotten support in the converter, so thanks for that. And the effort still continues as the opportunities rise. Next slide, please. So with different offsets and with quantization, essentially there was a gap, like offset 5, 6, 7. How do we go and convert them to offset 13? So that was a request. So the past two ONNX releases have been handling that pretty well to have support for the transition of these old operators into the new post-quantization kind of era of ops. And the ONNX Model Zoo example for end-to-end training, that is identified as a long-term intercept. And the next one with respect to federated learning for ONNX, there is no new ONNX operators that are required, so exploring different solutions which are very framework agnostic over there. For the improvement to shape inference, this is like the submitter is analyzing further on what to be targeted for the future. And the last two here, ONNX model provenance and the security, essentially you'll hear like a talk on this as well for responsible AI and explainable AI kind of features coming into ONNX. So the initial metadata fields have been defined, and there is a GitHub issue that has been filed as well. So the next one is related to how the model metadata will be used for mixed precision, and examples of that showing up in the zoo as well. Next slide, please. So as we saw, like there is a lot of couple of releases that have happened, 1.11, 1.12 that Mayank went over, and also Prashant highlighted like how the community has been growing. But we still need a lot of volunteers. It's a community project, so there is a lot of PRs that need to be managed. So request again to the broader community to have more people from your company join this effort, and we can take this further and much faster out into the industry. So please volunteer. All of you are doing that already, but encourage more people to do so as well. Next one. So again, please continue to stay engaged and your contributions to ONNX and its related projects. So there are different resources, the website, GitHub, as well as Slack channels. Slack channels, you'll see like so many of them relative to different topics. And the ONNX calendar also has a meetup for our steering committee meetings as well as the other SIG working groups, so that can be picked up from there. And do sign up for the mailing list as well as follow on Twitter. Thank you. Questions? Probably I'll invite back Prasant and Mayank if you have questions.
I think because we're running short on time, we have
Oh, okay.
questions for later, so connect with them later and ask questions online. So next we have the SIG and WG area updates working group.
Good morning, everyone. Thanks for coming. And
Come closer over here so the video can see you speak virtual people.
I need to.
Yeah, like over here.
Sorry.
That's right.
Good morning, everyone. Thanks for coming. There has been 2 ONNX releases since we last met. The latest one is 1.12 done by IBM. So let's give it a round of applause. And the contributors have made many, had added many new features to ONNX and keep making ONNX better. Chip inference has been improved. At operator level, quantized linear has become more stable to handle missing optional input. Error. Okay. Is that okay? Yes, sorry. Error checking for incorrect permutation was added for transpose. Chip inference for constant of shape is simplified, and the chip inference for expand was improved such that symbolic shape is used. Gather and shape are now utilizing result from data propagation. This last improvement was made possible by extending info shape API to expose result from data propagation. It helps PyTorch exporter to utilize ONNX chip inference functionality. And chip inference for local functions was added in release 1.11 and further enhanced in the latest 1.12 release. Next slide. ONNX generates test data for downstream applications to validate its implementation. In this current release, node test data is generated with a deterministic offset version. By default, the latest since version is used, and it is possible to select a offset version other than default if needed. And we have updated all the test data with this latest behavior. And because of this deterministic measure, we are able to validate test generation in all CI pipelines. CI systems for Linux release has been changed to many Linux 2014 because earlier version is no longer supported. We have dropped the support for x86 32-bit Linux, and the release packages for Python 3.10 were added to the release. We no longer produce packages for Python 3.6. And there are 2 important releases added. Model Composer can be used to creating and combining models out of several graphs and models. And the Function Builder can be used to construct function operators. It is impossible in this presentation to list all the improvement made by contributors. Here is just a overly shortened list. Initializers are decoupled with input such that a virtual converter can reliably convert models across any offset versions. And with a few additional bug fix, model converter has become more stable. In the repo, Python code is modernized with type annotation, showing our aim for the highest coding standard. The model parser has been improved to support greater grammar, and there are tons of fixes and documentation updates. In the next, we plan to provide a better support for ONNX releases. We realized that from our experience that the major risk factor for release delay was due to breaking changes that were detected by the runtime while building the release. So to alleviate this, we will plan to provide a CI pipeline for the runtime to automatically detect any breaking changes while doing a release, and so that early action can be taken. And we will also continue with our focus on shape inference improvement. And last but not least, we will continue to provide the infrastructure and architecture support for operator data processing and other special interest groups. And thank you.
Hi, I'm Rama, and I'll be presenting the update on behalf of the operator SIG. Thank you. Hi, so can you hear me? Okay, thanks. Yep, good. Yes, next, yeah. Since some of you may be new to ONNX, let me give a quick summary of the focus of the operator SIG. The ONNX spec, as Prashant earlier said, breaks into two parts. One is the IR and its semantics, and the second key part is the set of operators that constitute part of the spec. And the operator SIG focus on the second part primarily. And the operators are organized into domains, and there are two domains, the ONNX domain, which focuses on DNN operators, and the ONNX-ML domain, which focuses on classical ML operators. And these are versioned, and the SIG mostly focuses on how to evolve this set of operators, adding new operators as needed, and clarifying operator specs, and making changes to them as and when needed. So let me give a quick update on the changes that were introduced in the last two releases. The two new offsets, offset 16 and 17, were introduced in the last two releases. So in terms of the new ops introduced, we have grid sample, which is used in spatial transformer networks, layer normalization, which is widely used, for example, in language models such as BERT. Signal processing ops, basically DFT or FFT, they have been widely requested, and they are used in audio models. And sequence map, which was proposed by the pre-processing work group, which enables us, for example, to handle batches of images, for example, of varying sizes, if you want to pre-process them and convert them into a format required for a specific model like ResNet 50. And most of these are functions, except a grid sample and a few others, but there's a plan to promote them to be functions soon. And some of the existing ops were also updated. So for example, scatter op was updated to allow support for duplicate indices, where you can say the values specified for duplicate indices should be summed up, for example. And support and some of the ops were extended to provide support for types such as bfloat16 and optional types. And RO align had a minor update to adjust for a variation between different frameworks where the results were different, half by half a pixel. So yeah, let me, in the remaining few minutes, let me describe some of the plans going forward. And as I remember, the key goal for the operator SIG is primarily to have a clear and unambiguous specification, and there is room for improvement here, and we do need to improve the documentation for the spec for various ops. And as to the remaining goals, there is really a trade-off here, because on one hand, we would like to have a compact specification that is a smaller set of primitive ops that makes it easier to develop a new backend, for example, on a new hardware, and basically make it much easier to implement ONNX on new settings. On the other hand, we also would like to support the new kinds of models that come along, even support encoding pre-processing and post-processing logic in the model itself. And this leads to a desire to add more ops to the spec, basically. And the desire for efficiency also leads to a desire to add more complex composite ops that are coarse-grained but can be implemented efficiently. So there's a tension here, and we basically need to strike a balance between these two. And one of the key techniques we use to deal with this challenge is the notion of ONNX functions. And an ONNX function is essentially an ONNX op whose semantics is specified by in terms of other primitive ops. So effectively, this function definition provides an executable specification for the op, thereby improving the spec clarity, reducing ambiguity. But it also provides a default implementation so that it makes it easy to build a new backend. At the same time, when efficiency demands it, you can build a specialized kernel in specific backends for these ops, allowing us to balance these conflicting requirements we face. Going forward, one of our goal is to reduce the set of primitive operators, basically by promoting them into functions. So that we have identified around 25 to 30 of existing ops that can actually be promoted as functions, and we plan to do that. And one of the interesting new directions we are planning to take is to enable authoring ONNX in Python. And have a tool that automatically converts the Python function into an ONNX function proto, which is the serialized IR representation for functions in ONNX. And the plan is to also allow, use this as a way to debug using standard Python debugs, for example, the definitions of functions and to understand them. And so the plan is to use a subset of Python we call ONNX script to enable all of this. So let me give some example, a few examples. Here you see a function definition in Python for the well-known Jelu activation function, and the plan is we define the function in Python this way, and the converter will automatically generate the Jelu function definition. And as you can see in ONNX, the real function definition expands into a lot more operators and is less readable, but the compact specification is easier to author and also to read and understand. This is another example that illustrates the use of control flow. So for example, a dropout, which is a standard op in the Python spec, can itself be specified as a function on top of a random uniform generation. And again, the use of control flow makes it, Python control flow makes it easier to naturally and compactly specify the semantics of these ops as a function. And so this just illustrates the use of standard debuggers to understand these function definitions too. So for example here, you have a TIE example Python definition of an ONNX function, and you execute it just like you would execute in a standard Python by creating some inputs and invoking the function. And you can use the debugger to look at the values and understand the specs. So yeah, these are just some more examples for people interested, just to show how various existing ONNX ops can be compactly specified. That brings me to the end, and thanks for coming, and please do get involved with the operator SIG. As shown here, there's a Slack channel, and we have monthly SIG meetings that you can join, and we welcome your contributions. Thank you.
Thank you so much. Next up, we have Kevin Chen.
Hi, Faith. Can you hear me?
We can hear you.
Okay, great. Let me take control. Okay, great. Yeah, unfortunately, I could not make it to the meeting in person, but it's great to see all the participants here. So my name is Kevin. I've been involved in the ONNX community for the past couple of years, and today I'll be giving an update for the converter SIG and all the work that we've done since the last time we've met. So for the outline of this presentation, I'll be going over the converter update. So first, I'll be going over the front-end converter updates, which mainly deal with DL framework into ONNX model conversion. And for these front-end converters, I'll be going over the PyTorch-ONNX, TensorFlow-ONNX, and sklearn to ONNX converters that we have. Next, I'll be going over the backend converter updates. So these backend converters mainly deal with ONNX model format, translates them into a backend runtime framework where actual inference is run on the ONNX model. And for these backend converters, I'll be going over the ONNX-TensorRT as well as the ONNX TensorFlow converters. Next up, I'll be going over the roadmap for the converter SIG. And finally, there'll be a get involved slide for those of you that wish to participate in the converter SIG anytime after this meeting. So the first converter I'd like to go over is the PyTorch-ONNX converter. So the latest release that will be coming out very soon is PyTorch version 1.12, which supports ONNX exports up to ONNX offset 16. So there has been a bunch of new features added in this release, and some of the highlights include the ability to export neural network modules specifically as ONNX local functions, and this allows specific backends to target these functions specifically for accelerated inference. There has also been a lot of new ops support. You can see the full list listed there. And we've also added the ability to export ONNX bflow16 and optional data types, as well as added support for exporting quantized models, along with exporting models trained in mixed precision with Apex02. So for any users that are working with these new data types or working with quantized or mixed precision models, we recommend you to try out the new PyTorch exporter and see the updated workflow into converting to ONNX. Finally, we've added support for A10 fallback for non-CAP2 backend, and any user could see the full list of A10 supported operators in our documentation online. Finally, if this piqued your interest, we have a separate talk by Bowen later today at 1:35 p.m. Where he will go a little bit more in depth about all of the changes we've made in PyTorch 1.12. Next up is the TensorFlow to ONNX converter, and the latest release here is TF to ONNX version 1.11.1, which supports exporting to ONNX in offset 16 and TensorFlow versions up to TensorFlow 2.8. So the highlights here is that the default offset export version has been updated to 13, and there are a few new ops that are now able to be exported, including TF-lite batch matmul, TF-lite matmul, tensor scatter add, and random int. In addition, we've improved model export for Q2Q model, as well as general improvements for export for models trained in TF-lite. So again, if you're using Q2Q models or if you're using TF-lite, we recommend checking out the latest release for the updated workflow into exporting to ONNX. Next up is the sklearn to ONNX converter. So the latest release here is sklearn to ONNX 1.11.2, which supports ONNX export up to offset 15. The highlights here is that we've added a new up support for SGD1 class FVM. We have also a bunch of bug fixes for previously supported ops, as well as improved library import performance across the board. So we recommend users to update to the latest version for improved user experience when converting sklearn models into ONNX. Next up, I'll be going over the backend converters. So the first up is ONNX to TensorRT. So the latest release here is ONNX-TensorRT 8.4, and we support importing ONNX models up to offset 17. There are two new ops added in this release. So now we can import models using shrink and XOR, and there has been improved support for and bug fixes for these following ops: argmax, argmin, range, delu, gem, and einsum. Finally, we've improved support for dynamically shaped models, and we have general performance improvements across the board. So we recommend any new users and recurring users to upgrade to TensorRT 8.4 and start benchmarking with TensorRT to see what sort of performance improvements you could get when running ONNX models. Next up is ONNX TensorFlow, and the latest release here is version 1.10, which supports importing ONNX models up to offset 15 and supports TensorFlow versions up to 2.8. For new ops support, ONNX to TensorFlow actually supports the entire offset 15 ops spec, at least partially, as well as supporting ONNX optional data types. So again, for any users with models that are using offset 15 or lower and are using ONNX optional data types, we recommend using the latest version of ONNX to TensorFlow to import your models and do any new benchmarking there. As for the roadmap, the converter SIG had a few short-term and medium-term level goals. So for the short term, we wanted to improve our ONNX operator documentation support matrix across all of the converters. And this has been done over the past year across all the converters. So this is a very good improvement. For the medium-term goals, there are two main things that we want to focus on. So one is setting a minimal offset support across all the converters. So there has been discussions that previous offsets should be deprecated, and we are working on formally proposing deprecating offsets less than 9 as a starting point, and we can move on with the offset deprecation in the future if this goes through. Secondly, the other medium-term goal we have is to improve community-driven tooling. We've seen across a lot of converter repos, as well as across different companies, there are a lot of ad hoc implementations for a bunch of utility tools, such as fuzz testing, shape and type inference for ONNX models, quantization tools, and constant folding across ONNX models. And we want to work together with the community, as well as the ARC Infra group, to help start standardizing some of these tools and getting them contributed back into ONNX so that users and the converter users have have a one-stop shop for all of the utility functions that they may want to use. Finally, there is the perpetual goal across all converters to constantly improve, both in terms of bug fixes and improved operator and offset support. And for PyTorch specifically, one big item on the roadmap is that improved support for PyTorch models with lazy tensor and autograd functions are in the works. So definitely be on the outlook for that. So finally, feel free to get involved. So any quick feedback, feel free to join us on Slack in the ONNX Converters channel and drop by a quick comment or start a thread. For those that want to get involved a little bit more in depth, feel free to subscribe to our ONNX Converters SIG mailing list, where we send out invites for monthly meetings. So please subscribe if you want to get involved in that. And finally, we have a very amazing community across all the converter repos. Don't feel shy to open up issues or start discussions across GitHub, because we always welcome new contributions and new discussions, and we are very welcoming to any users that want to get involved in ONNX. So thank you. That concludes the ONNX Converter 6 for updates for today. Thank you all for listening.
Thank you so much. Next we have Jackie.
Yeah, I think I turned on, right, yeah. All right, thanks, Kevin. So I'm the new SIG lead of ONNX Model Zoo and tutorials. So today, updates since that workshop, and I'm Jackie from Microsoft. So today I will, we have two parts. So first I will talk about ONNX Model Zoo and then ONNX tutorials. So yeah, so before I jump into details, so let me introduce ONNX, what is ONNX Model Zoo. So ONNX Model Zoo is a collection of pre-trained and state-of-the-art like machine learning or deep learning models, which were mostly contributed by ONNX Community. And right now there are 40 kinds of ONNX models and 168 models in total with different kind of ONNX versions, including 35 vision-based ONNX models like image classification, object detection, super resolution, and also there's 5 models about machine comprehension like BERT, GPT-2. So yeah, and for what is ONNX tutorial? So ONNX tutorial is a place that have a lot of documents, notebooks demonstrating how ONNX in practice for different kinds of scenarios like different framework platforms and how they can work with different kinds of device types. Yeah, so I will talk more details about ONNX Model Zoo first. So we have a lot of new quantized models, which is mainly contributed by Intel. Thanks mainly from Intel, she contributed a lot of integer 8 models in ONNX Model Zoo, and including like both vision-based and text-based models. And one thing I want to highlight is that so we improved the test coverage at this moment. Like we have a routine CI in ONNX repo, like keep running the latest ONNX tracker and ONNX shape inference with all Model Zoo models. And like right now, like all of them are passed. And there's only some ancient models which is still using offset 3, so they don't have the shape inference function, so we cannot verify in ONNX. Otherwise, they are all passed by the latest release, ONNX 1.12. And next, one thing I would like to highlight is that recently we fixed a lot of broken test data set in ONNX Model Zoo. So right now that we have verified that all the models, most of the ONNX Model Zoo models can pass ONNX runtime with CPU per byte, and there's only one model failed. Then let me summarize what we did for the improvements since that workshop. So we did a lot of CI improvements because we introduced more quantized models, so we need to make the CI to take the right machines to run the test for quantized models. And as I mentioned in the last slide, we fixed a lot of broken test data set. And also we collaborate with Hugging Face team that we like accomplish a Gradle app, which is a Python web app to demo machine learning models. And I'll show you in the next slide. So, so Gradle is a web interface. And then we like host ONNX Model Zoo models in Hugging Face space. And then we use ONNX Runtime as backend engine to inference the accurate result. And then finally, it will show a great result on the web. So meanwhile, for ONNX Model Zoo, like we can also like have a link to redirect like certain ONNX Model Zoo models to Hugging Face space, and you can show some demo there. And they have a tutorial like how to do it in their Gradle website. And in Microsoft, we also I have also just published a blog in our Microsoft open source cloud blog. Next slide, please. So here I will show a quick demo to you. Could you, yeah. So like, as you can see, it's a website. So after we run some easy Python code, we can just upload some image on the left. And from the right, you can very easily, okay, the website will tell me, okay, there's a typecast there. And the only thing we need to do, just write like a couple of easy Python code here, like do some image processing, and then just feed the image to ONNX Runtime, and ONNX Runtime will inference the output result for us. And the Gradle will show the result on the web. And also they provide some community functions that you can make a pull request or start discussions about this app. Next slide, please. Yeah, thanks. So talk about some roadmap about Zoo. So like Kevin mentioned in his slide, we want to use like upset 3 models because they even cannot be run by ORT and they don't have shaping business function in ONNX. And also we will keep improving our CIs to verify ONNX Model Zoo models. And also we like looking for more models contributions, including quantized models, and perhaps currently there's no training example models there, but I think we can like have a first training example models in the future. Next. Yeah, then I will talk about ONNX tutorials. So yeah, for ONNX tutorials, mainly we finally introduced the CI there because there are a lot of deprecated URLs. So like right now, if you publish a new notebook or document there, in the CI it will automatically it will validate the URLs for new PRs, and also that we will weekly to go through the whole repos to check all URLs there, just in case that some URL is deprecated. And also we run some Python formatters to clean the notebook. And yeah, for the roadmap, I think here is just we want to keep polish the old tutorials, and in the future, I think we will prefer like URL redirections to other tutorials. Okay, yeah. So that's why I want to like say welcome to contribute, and actually the contribution of the new ONNX model is quite easy. Like you can first get an ONNX model, like it can be produced by any converter, and then you can use OR the test data set, including input output, and then just write README and pass the CI by ONNX run by ORT inference with CPU and get the right result, then your PR is ready to go. So yeah, if you have any topics you want to bring up, feel free to join us on Slack. There's a channel called like ONNX Model Zoo, and please help us to review the PRs. There are a few opening, and most importantly, I was looking for more volunteer approvers for SIG model tutorials. I think it's a very good opportunities for you to be visible to ONNX community, and also it's a good chance for you to learn ONNX, ONNX model, and ORT. Yeah. that's all I have. Thanks.
Thank you so much for those amazing updates. Next up, we have Jacqueline Anton.
Hi, my name is Joaquin Anton, and I would like to share with you what we've been working on lately in the ONNX preprocessing working group. Let me recap what the goal of the group is, and then I'll show you the work we've been doing lately. Today, ONNX models typically expect the input data to be already preprocessed. The complexity of that preprocessing pipeline may vary depending on the application. For instance, some typical steps in a computer vision application are cropping, resizing, normalizing, and transposing to a planar layout. Those preprocessing steps are usually defined vaguely or expressed in Python with some particular processing library. This lack of standardization creates a problem. Different data processing toolkits can have different definitions of apparently the same operation. In this example, we are comparing an image resize operation for two popular libraries, Pillow and OpenCV. As you can see, the results are obviously different. It all boils down to the fact that Pillow applies an anti-aliasing filter when downscaling, while OpenCV does not. Sometimes, small differences in the data preprocessing pipeline used during training and inference can result in a drop of accuracy. The second obvious problem with the current approach is the lack of availability of the libraries on the platform we are deploying. The goal of the group is to standardize the definition of those data preprocessing operations so that they are not ambiguous, and include those in the ONNX model. This simplifies deployment and avoids the potential accuracy problems we mentioned. Since the group was created, we've been working on different topics that will help us reach our goal. Some of the work is related to the general infrastructure that will allow us to include the data preprocessing in the model, such as being able to combine preprocessing pipelines with existing models, or being able to batch process samples, as we typically do at the preprocessing stage. Another line of work is related to the extension and creation of operators to enable our first end-to-end model, which we chose to be ResNet 50. Let's look at those items more closely. We proposed a set of composition utils that allow the user to merge two models or graphs by connecting some of the outputs in the first model to some of the inputs in the second model. The user can also decide to add a prefix to all the names in a given model to avoid name collisions when merging. The second topic was batch processing. A typical case when doing data preprocessing is to have a batch of samples that are not uniform in shape. In ONNX, we can represent that as a sequence of tensors. We do want to process each of the samples by applying a series of preprocessing steps. The typical result is a batch of samples that are now uniform in shape. Before feeding the network, we concatenate all those samples to a single tensor. To enable this pattern, we propose the sequence map operator. Sequence map is a generic sequence processing operator that can apply a graph to each element in an input sequence, producing a sequence as an output. We can use sequence map to apply our preprocessing graph defined on a one-sample basis to a batch of samples. Also, we are currently investigating ways to tag the preprocessing part of the model, so it can be later identified by backends. The current approach is to use a model local function as a single entry point for the preprocessing subgraph and mark it as such via metadata properties. To enable our first example, ResNet50, we are proposing a couple of extensions to the resize operator. The first one is an optional anti-aliasing filter to be applied when downscaling the input. This is necessary to match the behavior of some popular image processing libraries such as Pillow. The second extension is a keep aspect ratio policy that changes the interpretation of the target size. The policy can be to stretch, ignoring the original aspect ratio, which is currently the default behavior. Or it can be to treat the target size as either a maximum or a minimum size while keeping the original aspect ratio. The other operator we need for our first example is a center crop or pad operation. The operator we are proposing offers a convenient higher level abstraction, and it's implemented as a function that relies on the existing pad and slice operators. And that's all from us. We encourage you to join us on our Slack channel and our monthly meetings and share your ideas. Thank you for listening.
Thank you so much. We will take a quick 2-minute break now, and then we'll be back with the presentations.
Hi, my name is Joaquin Anton, and I would like to share with you what we've been working on lately in the ONNX preprocessing working group. Let me recap what the goal of the group is, and then I'll show you the work we've been doing.
Can you hear me?
We can hear you.
Perfect. So I'm Mauro Benici from Italy. I'm a developer and a data scientist. And I'm the CTO of Ghostwriter AI, a company in the field of natural language processing. And in the last year, I helped other developers and other companies to enter in the ONNX world. That means that the problem for them is that they have old models that need to be converted. So we know now that there are a lot of training tool, framework, inference tool, and many implementation for different devices. But there is a problem that is not always an idea when we started to ONNX, and this is the offset version. So the version that, as we saw, the importance of the operation functions that are implemented in the framework that we are using, or from the inference tool that we want to use. To do that, the wrong idea was that, okay, I have a model, and I can just see how to optimize, or just to export an ONNX, or just to use the ONNX runtime at the end of the process. So I have my model, and I wanted this model to be used on the cloud, on the device. Okay, at the end of the process, everything at the end of the process. This is not correct because a lot of things could happen. For example, the framework version that we are using doesn't support some operations, or the frame that we're using to do the training is not the same that if we have the offset for what we use as inference. So the right way is to start in advance to check what we want to use and the architecture that we want to create in our models, to be sure to do a terrible mistake at the end. When the error is easy to check is, for example, in the case of PyTorch. It's easy, of TensorFlow is the same, but I want to use the export my model on ONNX, and I simply receive an error. Okay, in this case, it's easy to check. Okay, I cannot export because if my model is just training or unproduction, it's a nightmare because I have to retrain everything. I have to change my architecture. But it's easy to check. Okay, I have to change. But what happens if my old model is written in a way that I do not receive at all an error? So I can export, the export works, but the result could be different. So I can have a text, I can just check all the pipelines from the exports, from the deployment, but what happens could be completely different. And so what happens in this DL? This DL is, we have to check the ONNX documentation before, at the beginning, or just to look on the page, not at the end when we have errors, but immediately. I'm using PyTorch version 1.10, it's okay. What are the limits for ONNX? What I'm using on my models to training it, and just to check. This is very important because also as we use other tools like ONNX Optimizer, we can see that, for example, it's my architecture that doesn't work. So I have to check also the issue on GitHub. I have to check if, I can change my architecture or my options to export correctly in ONNX my model. And what this seems to see is, okay, but it's natural to see the documentation. Just remember the documentation changes because not only the ONNX released new version, but also because the offset could be deprecated, removed. So all my pipeline need to be checked every time I update something or just I deploy on the cloud. Also, we use a lot of the ONNX runtime. And another idea completely wrong is if I just to use the best performance optimization options to have the best performance. This is an example. It's not true. If I use the quantization, but I use the CPU, I'm not optimizing my model, but I'm avoiding performance, and sometimes I reduce my accuracy. And this is true, for example, for the normal CPU, is not true for the GPU. Or if we are using the ARM processor, we can use other optimization. In this case, it's better also to be able to export, to just to use different models also in ONNX runtime. So a model that use the CPU, and other models that use the CPU with some notes of the version that we're using, and why are we using these options. Because also in this case, we don't have error, we don't have warning. Simple, our models is not working as we expected to. So it's not just not to be scared about the ONNX runtime. It's also just to say that checking the documentation in advance is possible because we have to design our model to be optimized. And the way is always the same: check the documentation and check the changes. Also, we can see here the operator are supported, but supported in different versions. So it could be something is changed, or perhaps in the ONNX runtime or other frame that you use to run, they are not optimized, or something is changed, and also is easy to check and to fix it, but we have to know. So ONNX and ONNX runtime are great tools, but remind that we are the mind. So we have to know what we are using. We cannot just use and hope that everything will be okay. So thank you. Thank you for having me. If you have any question, just no problem, I'm in chat. Bye.
Thank you so much. Next up, we have Daraj Perry from NVIDIA.
Hello everyone, I'm Dheeraj, a deep learning software engineer at NVIDIA, and welcome to today's session on INT8 Inference. In this session, we demonstrate an end-to-end workflow for deploying QAT networks using TensorRT. This talk is broadly divided into 4 parts. In the first half of the talk, I will discuss the basics of quantization and how TensorRT supports quantized networks through various fusions. In the second half, my colleague Gwena will talk about the quantization toolkit we have been working on and TensorRT deployment via ONNX. In the end, we will see an example and case study for ResNet QAT model. In this talk, we focus mostly on models that are trained with TensorFlow 2.0 framework. Let's look into deep neural networks quantization. So, what is quantization? Quantization is the process of converting continuous values into a discrete set of values using linear or nonlinear scaling techniques. In general, most machine learning models are trained in FP32 precision. Higher precision is necessary during training for fine-grained weight updates, but it's not usually necessary during inference. It can also hinder the deployment of AI models in real time and in resource-constrained devices. This is where INT8 can help. INT8 precision offers a faster inference and also lower memory footprint. There are clear benefits for converting an FP32 model into an INT8 model. However, there might be trade-offs with accuracy. In the context of this talk, when we say quantization, we refer to FP32 to INT8 quantization. And by dequantization, we mean INT8 to FP32 conversion. There are different quantization schemes by which floating point tensors can be converted into lower precision. One standard way to express a real value in terms of quantized value q is r equals to s times q minus z, where s and z are scale and 0 points. These scale and 0 points are together referred to as quantization parameters or q-params. Q-params can be determined either via post-training quantization or PTQ and quantization-aware training or QAT. Let's discuss PTQ and QAT in detail. In post-training quantization, we start with a pre-trained model and run it on a calibration dataset. A calibration dataset can be a subset of training or validation data. During this execution, we gather the layer-wise statistics such as min and max values of the input tensors for each layer. This min and max values are referred to as dynamic range for each layer. The dynamic range is then used to compute quantization parameters for that particular layer. Now we use these Q-params to quantize the whole network and perform inference in INT8 after performing PTQ. In quantization-aware training or QAT, we start with a pre-trained model and introduce something called QDQ nodes or quantize and dequantize nodes at desired layers. QDQ nodes is a single node in the whole graph which quantizes and dequantizes. That is, it converts FP32 to INT8 and INT8 back to FP32. The QDQ node basically simulates the quantization that is performed during inference when the whole model is converted into INT8. Once these QDQ nodes are introduced in the graph, we fine-tune the graph for a small number of epochs. This is usually like 10% of the training, for example. The goal is to then learn either the Q-params or the model parameters or both that can reduce the accuracy drop between the quantized model and the baseline pre-trained FP32 model. Now that we have seen what PTQ and QAT is, let's quickly go over some of the differences between these two techniques. PTQ is usually fast. It depends on the number of calibration data samples being evaluated. QAT is a relatively slower process to obtain the final quantized model. By the nature of the scheme, QAT requires fine-tuning while PTQ does not. With PTQ, we have less control over the final accuracy of the model. However, in QAT techniques, we have more control over the final accuracy since we learn the model parameters during training to minimize the accuracy drop. Finally, in the context of TensorRT's PTQ, we have less control over which layers are quantized, whereas in QAT we can choose which layers to quantize. Now that we have seen the differences between PTQ and QAT, let's discuss how to perform QAT in TensorFlow 2.0. One of the ways to perform QAT is to use TF-mod toolkit released by Google. This toolkit implements TF quantization recipe, which we will discuss in the later slide. When we refer to a quantization recipe, you can think of it as a particular placement of QDQ nodes in the graph. This toolkit supports full quantization of the model and partial quantization, where some layers can be quantized by using layer class attribute. Fake quantization, or the process of quantize and dequantize, is performed using fake quant with min-max vars op, which performs asymmetric quantization in TF-mod. In contrast, at NVIDIA, we have been working on a separate TF2-based quantization toolkit built on top of TF-mod. There are some important differences to TF-mod that we would like to highlight. Our toolkit implements NVIDIA's quantization recipe optimized for TensorRT for model acceleration. We can also quantize layers by using both layer name and layer class as attributes. Users can also implement pattern-based quantization where they can identify patterns in the graph and place QDQ nodes around them. And one of the most important differences is that the quantization is performed using quantize and dequantize V2 operation. This operation performs symmetric quantization that is recommended by TensorRT. To get the best performance for a QAT model on a GPU using TensorRT, we recommend to use NVIDIA's quantization toolkit. As mentioned in the previous slide, our toolkit differs from TFMod in terms of where we place these QDQ nodes. In our toolkit, we place these QDQ nodes at the inputs and the weights of a layer in the network, whereas TFMod recommends to place these QDQ nodes at the weights and the outputs of a layer. Now, let's look into how TensorRT optimizes these models. TensorRT is an SDK which provides a compiler and runtime for high-performance deep learning inference. It has a plethora of strategies for optimizing the model. One of the important optimizations among them is layer fusions. Different types of layer fusions happen in TensorRT. For example, point-wise fusion, convolution element-wise fusion, convolution and pooling fusion, etc. In addition to these, we now have dedicated fusions for QDQ nodes. Let's discuss them in detail. In this slide, we see how we place QDQ nodes at different layers in the network. In general, for layers which have weights, such as convolution or dense layer, we place QDQ nodes at weights and inputs of the network, as shown in the left. For non-weighted layers, we just place the QDQ nodes at the inputs. For example, in the residual add function, we see that the QDQ nodes are placed in the residual section of the add layer. For a concat layer, we quantize and dequantize all the inputs that are going into the concat op. And for different types of poolings, such as average or global average pooling and max pooling, we add QDQ nodes at the inputs to this op. Internally, TensorRT's graph optimizer performs a process called QDQ propagation. QDQ propagation is a process of moving around Q and DQ nodes to ensure maximum portion of the graph runs in INT8. Forward and backward propagation occur until they reach a layer that is not supported in INT8 precision. For example, in the top figure, we see a quantized input followed by a DQ node and then a max pool node. The DQ propagation will happen and the DQ node is pushed after the max pool layer. Hence, the max pool will run in INT8 precision. In the bottom figure, we see that a Q node is followed after a max pool layer. In this case, Q propagation will happen and is moved before the max pool operation so that the max pool runs in INT8. Other examples of quantization fusions in TensorRT include average pool quantization and element-wise addition fusion. On the left, you see a quantizable average pool layer is surrounded by a DQ layer and a Q layer. The input is an INT8. After fusion, all the three layers are replaced by a quantized average pool layer which will run in INT8 and output an INT8 tensor. On the right, you see an example of a quantizable operation which is add. The DQ nodes around the add layer are moved beyond the add and are fused with the output Q node so that the add operation is performed in INT8 and results in an INT8 output tensor. Now, let's take a look at a residual block quantization fusion. In a residual block, an input is passed through a series of convolution batch norm and, if possible, ReLU operations and is one of the inputs to the add layer. And the same input is being passed through an identity branch, which is a second input to the add layer. Beyond the usual recommendation of adding QDQ nodes at the input and weights of the convolution, we also recommend to add QDQ nodes at the identity branch in order to get the best performance from TensorRT. The resulting fusions look like this. The DQ nodes of the weights and the inputs are being propagated beyond the add and are fused with the Q nodes after the add layer. This will result in the entire block running in INT8 convolution where the add is also performed internally in the fused kernel. And this results in an INT8 output tensor. Without the QDQ nodes in the residual add in the top branch here, the convolution will run in INT8, but the kernel outputs float values using the DQ nodes of the convolution layer. And then the add will then be performed in float. In order to optimize this, we strongly recommend to use QDQ nodes at the identity branch. In this slide, I would like to highlight the differences between a suboptimal fusion and an optimal fusion. In the figure on the right, you can see the classic example of the residual quantization that we discussed in the previous slide. Here, the DQ operators and the Q operators surrounding the convolution and add, everything gets fused and they will run in a single kernel where the convolution and add operation are performed. And the resulting output tensor would also be in INT8 precision. Whereas on the figure on the right has an extra set of Q and DQ nodes right before the add layer. These extra QDQ nodes will hinder the fusion opportunity in the graph. Here, the DQ nodes and the Q nodes surrounding the con will form as a one block and will be fused into a INT8 convolution operator. And the DQ node and the Q node surrounding this add operator will result in a single fused add block. Although both convolution and addition will run in INT8 precision, there would be two separate kernels that will be performing these operations. This can lead to a performance hit, and if there are multiple such patterns in the entire graph, this can lead to a poor performance in the model. So we should be really careful when we are placing QDQ nodes in the original graph. Please follow the TensorRT recommendations and the above slides in order to get the best performance for your model. With this, I would like to conclude, and I'd like to invite Gwena to discuss how we can insert these QDQ nodes in a TensorFlow graph and the TensorFlow toolkit that we have been working on.
All right, thank you so much. Next up, we have Alessandro from AMD.
Hi everyone, can you hear me okay? If there are any issues, please let me know in the chat. Otherwise, I'll just keep on going. So I'm Alessandro. I'm with AMD through the recent Xilinx acquisition, and today I'm also going to be talking about quantization. See if I can move these slides. Navigation.
Alessandro,
I don't seem
one
to be
moment.
able to
We are
move
going
the
to get
slides
the
forward,
slides
though.
back for you.
Can anyone among the organizer please unblock that for me, because it seems to
Yep.
be blocked.
Yep, we're getting it fixed right now, if you can hear me.
Okay, see, we are back to my slides, but I still cannot navigate with the buttons at the bottom left.
Yep, we'll get this fixed for you in just one moment. Thank you.
Thank you. Thank you. Thanks for the feedback.
Once the quantized and fine-tuned TensorFlow saved model has been obtained, in this section, we present a case study in accuracy and and please let us know if you have any questions.
Let's take a quick 5-minute break, and then we will come back to Alessandro.
All right, thank you. network, we managed to achieve on one of our RFSOC platform 1.7 billion samples per second of throughput and at less than 3 microseconds of latency, thanks to reduced precision. So it works, it's very effective, thanks mostly to quantization-aware training. In this presentation, I'm going to talk about quantization-aware training and just cover the extreme fundamentals of uniform quantization, but I'm going to be concerned with how we represent in our tools, in our workflows, low precision quantized neural networks. So just as for the very basics, it was also mentioned in the previous excellent presentation, you can think about quantization, in particular uniform affine quantization, as a combination of two functions. The quantized one, which maps a floating point value to an integer one by means of scale, 0 point as a choice of precision, as well as sign, which determines your clipping boundaries, as well as the quantized function, which maps your integer value back to a floating point representation. And the combination of these two functions is typically referred to as fake quantization, meaning a float-to-float mapping through quantization and then dequantization. The idea, as it was also presented earlier, is that you can then map this representation to an integer-only acceleration strategy to appropriate transformation and fusion strategies. And so currently, if you look at how quantization in ONNX is represented, in particular at 8-bit, you have two predominant styles. The QDQ one, which leverages quantized and dequantized nodes to represent fake quantization, and the so-called QLinear ops, which actually was the original way to represent quantized neural network in ONNX. It is more oriented towards representing already diffused operator, in particular typically with fused output quantization. It comes with limitation though, and the main issue when it comes to low precision quantization is that there isn't any standardized way to represent data quantized below 8 bits, nor at other precision like, I don't know, 12 bits or 16 bits, which can be relevant, for example, in LSTMs. And so our first suggestion for extending the representational power of ONNX is to leverage, for low precision neural network, is to leverage clipping. And the idea of this strategy is basically to maintain a retrocompatibility with all the existing libraries and tools around quantization, but to add an extra clipping function, which is already supported over integer boundaries between a quantized node and a dequantized node to represent basically the precision that we want to induce at that boundary. So for example, in this case, I'm showing here on the left to represent a 4-bit quantization, I'm clipping between -8 and 7. And the idea is that with existing tool, you can still get the correct result and potentially even up to 8-bit acceleration. And newer, smarter backends can also then potentially, by analyzing the integer boundaries, take advantage of the extra acceleration opportunity offered by the reduced precision, and so go down to actual 4-bit acceleration. One of the issues of this approach, though, is that it extends only as far as quantized linear allows to go as an operator, and currently quantized linear is limited to only an 8-bit output. And it also comes with some other limitation. For example, something that we are sometimes concerned with in our line of work is adopting different type of roundings, which is something that you cannot easily represent with this style of representation. And so something that we've been working on for a while now is this quantization, ONNX quantization dialect that we like to call QONNX, that basically tries to simplify the quantization representation by merging this sequence of operation for fake quantization into just one node. But at the same time, it extends it to a wider set of scenarios by taking, for example, a broadcastable bit tweet as input, as well, as giving you option around different type of roundings, as well as having, options for binary quantization and so on. And this format is something that we have been leveraging a lot also as part of our efforts for deployment on FPGAs, in particular as part of this common effort called the fast machine learning. And so we have available a variety of tools for dealing with the QONNX that integrates with the ONNX Runtime, as well as various pre-trained low precision models that you can find in our model zoo. QONNX is already integrated as part of the Brevitas PyTorch quantization library, which is something I work on that we leverage a lot internally and with customers. And QCDQ is also going to be integrated in the next release. We use QONNX a lot as part of our as part of two libraries for data flow inference of low precision neural network on FPGAs, so the FIN toolchains and the HLS4ML toolchains, which count very good adoption in the FPGA community. And the format is also being adopted both by the Hawk quantization library as well as by QKeras by means of a converter that we are currently implementing. We obviously would love to work with the broader community on this topic, and particularly on QONNX, so feel free to reach out if you are interested in learning more. And thanks for the time.
Thank you so much, Alessandro. Next, we have Daniel from Mithril.
Okay. Yes, can you hear me?
I can hear you.
Okay, great. Thanks for welcoming me today. So I am Daniel Wynn, the CEO of Metro Security, and I will show you how we can deploy ONNX models with privacy guarantees. Can I share my screen? Yeah.
Did you take control at the top?
Where is Oh yeah, thanks. Okay. Does it work? Yeah. You get used to it. Okay. Yes. So the issue we address at Metro Security is the fact that we might want to deploy AI models, especially in a cloud setup. For instance, imagine you want to use AI to screen patients using deep convolutional networks. But the issue we face is that when we want sensitive data to be analyzed by other parties, we need to trust them with the data, especially in cloud scenarios, where you need to trust both the AI companies that will deploy the model, but also the cloud providers. And sometimes for regulation, privacy, and security reasons, this can be an obstacle for the adoption of AI. And so you might think, what is the issue? If, for instance, I use TLS, isn't that enough? But we see that the problem is at the last mile during analysis. So for instance, we can imagine that this hospital wants to use this COVID screening as a service. So they get the data locally on the device, they can encrypt it. Then what happens is they will send it through regular channels, for instance, a TLS channel, and the data can be sent there, and it will be decrypted. So this is like regular stuff, but this is a problem. At that specific moment, because we needed to decrypt the data is available both to the cloud provider and the AI provider. And it is because at the last mile, the data is accessible, any malicious insider can dump the data, get access to it, and therefore the data owner has no longer guarantees that his data is safe, because at that specific time when data needed to be analyzed by the AI, it is exposed. And because we have no control of that, this is a huge issue to trust external parties with the data for AI training or deployment. So that's why at Metro Security, we have developed Blind AI, which is an open source and secure solution to deploy ONNX models inside what we call secure enclaves, which are solutions that leverage hardware to protect data. So what is the difference? Data will be decrypted inside this enclave, but the idea is that this enclave, which are hardware-based technologies, provide isolation and encryption of the memory content of the enclave, and so any dumping attempt for the outside will abort. But while data is still inside the enclave, you can do whatever you want, including applying, for instance, an ONNX model. So this way, you can analyze that inside a secure environment, but it's not accessible to the outside. And for instance, here you can get a result. You can then re-encrypt the data and send it back to the user so that they can benefit from it without having to trust a third party with their data in clear. But the best part is that they did not need to deploy the solution locally. They could resort to an external cloud solution. So it's very easy for them to be onboarded. And for the AI provider, it's very easy to maintain and sell that solution. So how does it work in practice of architecture? The idea is that we have an ONNX engine. We are using Tract, which is Rust-based ONNX engine initially for embedded devices, but we've modified it to make it work inside a secure enclave, and then provide some networking abilities for data to be analyzed. And then we have wrapped everything inside a Docker image, and then we have several Python, several cloud SDKs to securely consume a remote model. The idea is that by leveraging the ONNX format, we make it easy to deploy AI models with privacy guarantees. You can easily deploy our Docker images, for instance, in Azure using a confidential VM. Then with our Python SDK, you can securely upload your ONNX model. For instance, here we put a Distilbert model inside of this. And finally, with the same Python SDK, you can securely send data to be analyzed without the third party having access to your data. And really, by leveraging the ONNX expressivity, you can see that it's quite smooth and resembles existing solutions. And because ONNX is able to cover a lot of models currently, thanks to its expressivity, we're able to cover a lot of use cases. For instance, baggage screening at airports. And for instance, for that, we help a client use a YOLO model. We also help other people use NLP to analyze medical documents to save times for hospitals. In that case, they use a BERT model. And finally, we can also cover, for instance, facial recognition, because our model also covers, our loader also covers ResNet's model. And so what do you see in terms of difference of speed when you are inside an enclave? So here I show you different models that are quite used in practice. And the inference time with our inference engine in Rust outside of the enclave and the inference time inside the enclave. So you can see that there is an added, let's say, latency, but it's let's say, reasonable given the added protection we provide. And we can discuss this later. But also, one thing I did mention that we are actually able to put huge models inside enclaves. And we have done testing, for instance, with a GPT model with 3 billion networks, and it does work under a second. So it's very promising to enable people to consume AI models that will not be able to deploy on-premise, but still send data and have protection guarantees on their data. And finally, the good thing with using ONNX is that you need a minimal code base to apply AI models and control if you're having, a generic Python solution. By using just an inference runtime, you can have a little code base that is better for security reasons, and also you can reinforce each operators to make them what we call side channel resistance, which means that we try to avoid leakage to the outside, even though we are using a secure enclave. So I am done. Yeah. So if you are interested by our solution, you can contact us, and you can also have a look at our GitHub. Our solution works from end to end, and we have various scenarios that we can cover. I think I've left some time for questions, but if not, I can also dig deeper into the technical security details, or I can stop here.
Thank you so much. If people have questions, please put them in the chat, and if you could answer those questions in the chat, that would be awesome.
Okay.
Next up, we have Intel, and we have 5 speakers for there.
Okay, excellent. Am I audible?
We can hear you.
Okay, sounds good. Thank you.
I think we may have lost you. 1 second.
Okay.
Are you able to take control of the slides?
I am now. Thank you.
Okay, great. Are you the only presenter, or are your?
I have 2 other presenters, co-presenters with me today. I'll be controlling the slides. So.
Okay, great. Thanks so much.
Okay, sounds good. Thank you. Awesome. Okay. Hi, everyone. We're really excited to be here today to speak to you about responsible AI in ONNX, specifically looking at topics around metadata, model cards, and provenance. So I'm here with my 2 co-presenters today, Gabe and Bhargavi, and from Intel, and we're going to be walking through what a proposal for incorporating metadata-related elements in ONNX would look like, and what we can start to do as a community to make this a reality. So first, let's kind of start out with what's been done before and how this proposal really got started. So the first proposal was really targeted around enabling machine-readable AI metadata in ONNX. And as we'll talk about throughout this presentation, we see a number of different opportunities for being able to enable metadata-related elements as part of ONNX Runtime and the broader ONNX related items and tasks and implementations. So some of these key points are around being able to track provenance and other relevant characteristics for being able to essentially be able to identify how a model and the data that is associated with it is moving over time and being able to evolve given a specific use case. There are a couple of other opportunities as well that we see that we'll elaborate on briefly as part of this presentation in terms of identifying models with mixed precision, facilitating runtime metadata checks as well, where we start to connect this back to the pre-processing element of ONNX graphs, and also enabling queries on model zoos and hubs for filtering for relevant use cases. So this is just a key subset of the different capabilities that we can see that could be enabled having metadata as part of ONNX. Now here, as part of a quick timeline of activities, this team presented the roadmap proposal in October of last year to the ONNX Steering Committee, where the first suggestions were really put forth for the first cut of relevant fields related to metadata, essentially being able to elaborate on the context and say, okay, what do we really care about here when we say metadata, and what are some of the key elements that we would want to balance out? There was also some very specific machine-readable formats and query languages that were proposed as part of this roadmap, kind of stand-up proposal. As part of this presentation, we now want to take this opportunity to extend the proposal and start to think about the broader picture around model creation and consumption. So as part of this, what we're going to start off with is recapping the motivation and context, think about why we need metadata in the first place for responsible AI. We're then going to present our proposal with a new concrete end-to-end design where we cover the creation, querying, and visualization of metadata, apropos model hubs and zoos. And then we want to solicit your contributions, see and get your feedback on this and identify if there's any particular items that this community would like to collaborate on. Perfect. So to start us off, ONNX needs responsible AI. And as I previously iterated in the prior slide, metadata is one of these key elements that's really coming up with a lot of different concepts tied to it related to provenance and other aspects. But if we take a step back and start to look at what exactly is metadata, the forms it takes, and why do we need it embedded as part of ONNX, we see that metadata is a key enabler of responsible AI and explainable AI today. Again, the provenance related aspects are definitely a huge benefit where you're able to track a model, and again, the metadata associated with it. There's also the characterization of models as well that we'll briefly cover as part of this presentation. All of us may have encountered, these different forms of performance characterization that we're starting to see with machine learning models, especially that's where explainable AI is starting to come into place, where you have these technologies for debugging models or for human comprehensibility, etc. And we're seeing that metadata is something that is really a central part of it, can take multiple forms, mean multiple things, and help with these two aspects. There's also the idea of narrowing down onto failure modes as well to help identify why and where an AI model failed. Also in different environments, whether that be offline or directly during runtime, being able to do this type of monitoring for pain point identification for AI systems. Now, the current emphasis today is on human comprehensible metadata, and model cards are a very nice industry standard example of this, where you have this ethical report or documentation that's a couple of pages, talks about quantitative analysis, limitations, etc. But metadata is helpful if it is machine readable as well. And here we have a very small pipeline on the slide showing how the process from generating metadata to importing and attaching metadata to a given model, whether that's local in terms of embedded directly within the model, or uploaded to the cloud or the hub as part of a human comprehensible format. These different formats can then take into place and allow you to start querying the metadata, start to form and understand some trends associated with the models and how they behave, what are some of the characteristics of them, etc. And finally, visualize this, bringing it all back together for the human in the loop stakeholders to be able to analyze and understand what's going on. So throughout this presentation, we're going to be elaborating on the different elements of this pipeline. And right now, I am going to switch the mic over to Bhargavi to take it on from here.
Thank you, Riva. Thank you, Ria. Hey, everyone. So I'd like to go over the existing work in this area about encapsulating metadata in models. So the example that you see in the slide over here, could you go back to the previous slide? Yeah, thank you. So the example in the slide shown is part of the TensorFlow Model Card Toolkit. So Model Card Toolkit is a collection of tools to generate metadata in the form of JSON schema, and it attaches to TensorFlow models. So there are APIs to visualize and generate model cards. Yeah, could you go on to the next slide? So ONNX protobuf has some support for metadata already in the form of key value pairs, as you see in the example as shown in the example in the slide. So we'd like to build on this support and extend this functionality to incorporate more machine readable metadata format using RDF, which is very standardized and widely adopted industry approach for representing metadata. And RDF is also powerful in the sense it would not only help define model characteristics, but also establish relationship among entities. Could you move on to the next slide? Yeah. So it follows a structured approach to define metadata. It is more machine readable, and we think we could, it should be easy to extend this functionality in ONNX. It also, RDF also has the flexibility to, it allows for decentralized metadata representation. It allows for querying metadata using Sparkle, a powerful capability that my colleague Gabe will go over in the next few slides. Not only metadata, machine readable metadata representation helps in maintaining transparency, but we believe it would be very useful to track provenance. It'll also help us answer questions such as when something goes wrong with the model deployment, it'll help answer questions such as what caused this model to have lower accuracy than expected. Was the data set updated? Was the right validation or test data set used? Or who trained the model? So answering, this approach would help answer such questions. Yeah, could you move on to the next slide? Yeah. So our initial proposal has a detailed description of the model provenance fields that we would like to include. You could find the link, GitHub link in the presentation below for a more detailed description of metadata. For instance, what training data set was used, what licensing was there, or what frameworks were used to train the model, details such as precision, whether it's an INT8 model or an FP32 model. Yeah, and I'd like to hand over the next slides to Gabe, who would be talking about querying metadata in detail.
Thank you, Bhargavi. Can you guys hear me? Yeah, good.
Yes.
Thank you. So as you can imagine, adding metadata, no matter how informative is to a model is only part of is kind of like the first half of the battle. Like querying the metadata, what you can do with models that are decorated with metadata is kind of where really the usefulness of having having this extra information should come into play. So here we're illustrating the kind of things that you would be able to the kind of information you'd be able to extract from models that have RDF the formatted metadata associated with them. So the RDF, as Bhargavi touched briefly on, is kind of like a development from the semantic web, and it came from requirements of mostly like library science and curators of information, like large quantities of information, like scientific papers, scientific libraries, and the creation of scientific data sets. So as part of that, part of that community generated this notion, this control vocabulary called fairness. Fair here being less having to do with fairness and more for what the semantic web community called identified as like 4 guiding principles to have data or data or digital assets being actually useful. And fair like stand for the letters of fair stand for findable, accessible, interoperable, and reusable. So here we're trying to put that to the test by illustrating the kind of queries that you could issue against the RDF encoded metadata using this fairness ontology. So here the first query at the top left of the slide, it just goes over, tries to identify from a collection of models which ones are best are suitable to doing NLP tasks on and that have been proven or that have been trained, especially on categories like that include sports, for example. So if you want to do sentiment analysis on an ongoing game or something like this, would allow you to identify from a large collection of models which ones are, to discover those that would satisfy this use case. The part of what the advantages of RDF that we find useful here is that it's kind of infinitely extensible. So this control vocabulary is not limited to like what it is that you want to some authority has decided to include in the vocabulary, but you can extend it as long as you made those ontologies also available online. So as long as there is a URL that you can dereference and use. So here we illustrate that kind of capability by in the second query, to the left, but at the bottom, a provenance task where you try to identify what is models or list the available models associated with determining where who created them. The who can be an organization or a specific person, and they group them by how big they are, where big is a measure of how many layers they have. Of course, like this is just kind of like not the only way to measure size. So but RDF and the query language, which by the way, like I should call it the query language for RDF is called Sparkle, and it's something that you're likely to find in things like Wikidata, which is the data that's the machine readable version of Wikipedia, like with the information that you would find in info boxes and so on. The third example here is it tries to illustrate, like again, like this extensibility by tracking things that have more to do with responsible AI. So if you would like to identify those models in your collection or in a particular hub that have specific and classify them or sort them by their carbon footprint, you can do this by using adding the specific constraint. Ria, could you move to the next slide, please? So for these two queries that are more try to illustrate more the responsible AI and the mixed precision tasks that could be associated with the metadata. So in the query to the left, it's we are trying to identify those models that were trained with data sets that have private personal information, or and just bear in mind that this is what the metadata author has stated, right? Like, so this is, there is no extra measure of like whether a model is responsible, does not exhibit a particular bias. That those are facilities that can be built on this, but right now we're just concentrating on providing the foundational blocks to do so. The query the query to the right is a similar thing, identifying mixed precision, but this makes use of an extra extensibility point that we have provided. Ria, would you move to the next slide? So this is all well and good, but the how to deliver this functionality it remained a question. So we have found, and we're working on a POC that provides the functionality that I just show you, extending the Hugging Face Hub API, basically by allowing the kind of queries that I showed you as filters, extending the filtering capability that the Hugging Face Hub API already allows. So we are the use model that we have in mind is kind of like a two-stage use model, where you first go from a large collection of models, you run this query, and then you identify a much smaller subset that may be useful to your task, and then you can do kind of like a double click, or consult more specific information that can be displayed in a different way. So for this, I'll hand it over to Ria to show what information I'm talking about.
Okay, thank you, Gabe. Perfect. So just wrapping up here in terms of the visualization, which is the final third element of the pipeline, speaking to what Bhargavi and Gabe had covered around the querying language and the context there. This is how we envision essentially the profile data will be presented in terms of being able to incorporate elements related to explainable AI, such as saliency maps or interpretability related techniques for different types of models, not only restricted to computer vision, but also just as the scope of ONNX is continuing to increase in the types of models and use cases, being able to also adopt some of those techniques here as well and incorporate them as metadata, extending on the existing support for metadata that already is currently there as part of ONNX. And to the right, we also have an example of, some plots that we might start to include around, model cards and bringing in the balance between what is machine readable or embedded within the model and what is queryable, and then what is kind of a document associated with the model, something that we found very intuitive as part of the Hugging Face model hubs as well, that we're very interested to see how we could potentially extend. So we can start to see the emergence of things like data and AI quality metrics as well, not just our traditional explainable AI related methods, to create a holistic picture of performance profiling, characterization again of these machine learning models that are coming from ONNX. So all in all, I do want to conclude with the call to action and reinforce a couple of key themes here. As I mentioned in the introduction, we have been building on the proposal that we presented in the October 2021 meeting in order to essentially cover a design around enabling machine readable metadata in ONNX. Today, we are presenting our extension of this proposal to consider a more concrete design around model creation and consumption, and then being able to cover the entire metadata creation, querying, and filtering from hubs kind of workflow, being able to leverage currently existing ONNX infrastructure as a key benefit of this. So we are preparing an initial strawman implementation, and we have more updates to come, specifically also from the Intel side. We're very interested in exploring technologies around the metadata creation part, which we didn't have too much time to get into here. We kind of jumped into the querying and the filtering components as well as visualization. But we have some technologies that are coming out there, particularly also in relationship to OpenVINO and ONNX as well. And with that, we would like to welcome collaboration and open dialogue. We want to know your thoughts on the types of metadata fields that we might want to include, how we might want to implement this, what's the right balance of transparency. We definitely welcome any of those contributions or dialogue to help develop these solutions. Finally, we would definitely like to see our proposal, which is available publicly as a GitHub issue on the ONNX repository, included as part of the ONNX 1.13 spec as well. So we're looking forward to collaborate with this team to make this a reality and help enable a lot of the other great topics being talked about today using metadata and provenance and these related concepts. With that, if we have time for questions, we definitely like to open it up. Otherwise, we're happy to answer any offline. Thank you so much for your time.
Thank you so much. Please put your questions in the chat and we can get answers for you there. Next up, we have Oracle.
Hello. Sorry, just let me get to the appropriate. Oh. Oh.
Make sure to hit take control, Adam.
I did, and then someone took it back off me. So.
Okay, one moment.
Yeah, it's dropped me somewhere in the presentation. I can't easily spot where I've ended up. Sorry.
No worries, we'll get it set up.
The perils of hybrid conferences.
Okay, now you're ready to take control. Thank you.
There we go. Thank you. So I'm Adam Pocock. I'm a researcher in the Machine Learning Research Group in Oracle Labs, and today I'm going to talk about ONNX and the Java platform. So one question, everyone's talking about Python today. Why would we want to support ONNX on the JVM or on the Java platform? Well, ML models are increasingly important in basically every application, and most applications, especially like large business applications of the kind we're interested in at Oracle, are written in languages that are not Python. So we could either get all those developers to move to Python, which doesn't seem very likely, or we could bring machine learning to them in the languages they work in, like Java or C# or JavaScript. Java is one of the largest platforms for building live software applications in the world. There's millions of Java developers, and we think it'd be good for the ONNX community and sort of the wider ML community to try and help them integrate ML into their applications by meeting them where they are in the JVM. So I've spent the past few years sort of building Java ML tooling both for ONNX and other ML libraries, and we'll talk a little bit about some of that today. So the first thing was the ONNX Runtime Java API. So this was something that was built in our group in Oracle Labs in spring of 2019. We contributed it to the upstream ONNX Runtime project in December. The binaries have been available since 2020. This is used in production in Oracle and some other companies. I believe some of them will be talking after me about their production use cases. So I'm not going to talk about that very much. And our goal is basically to provide the ONNX Runtime C API in Java. So it's easy to use and it's sort of idiomatic, and you can get all of the functionality that you'd expect. You can deploy all the models that you need to. We want to try and keep feature parity with all the other APIs. There's a few things that we're missing at the moment around custom memory allocation and IO binding, because it's difficult to sort of express pointers and native memory operations in Java. It's not really for that. But if there's something else missing or you need those features, please open an issue on GitHub and we can talk to you about it. Our aim really is that the Java API is a very thin layer over the C API with minimal performance impact. We have a zero copy path through from Java into ONNX Runtime for inputs. You have to do a copy on the way out, although we're looking at ways of avoiding that. But fortunately, your inputs tend to be a little smaller than your outputs. So your outputs tend to be a little smaller than your inputs, so it's less of a problem doing that copy. And you have to do a copy if you're on a GPU anyway. The API targets Java 8 and runs on all versions later than that. And there's no other dependencies apart from the ONNX Runtime native library, and that's packaged into it, so it's very easy to deploy. So we're going to look at a quick code example. It looks very much like the Python and the other APIs, right? We're trying to be simple and similar to other things. So you have to make an ONNX environment. You can control like a per environment thread pool there if you need to, or the logging. We didn't bother in this example. We're going to make some session options, set the number of threads that we're using, and then we load a model by reading an ONNX model in off disk, or you can read a byte array in from memory. This session exposes all the things that you would expect it to expose if you use ONNX Runtime in Python. You can get the metadata out. So this is a CNN on MNIST. So it was exported from PyTorch using the PyTorch exporter. There wasn't any custom metadata or descriptions because I didn't do anything fancy while I did it. You can see that the inputs, it's expecting a batch size, a single channel, and 28 by 28 pixels because this is MNIST. And we get back out some batch size parameter and then the 10 digits. So when we want to feed data into it, as I said, there's a zero copy pathing. You have to use a byte buffer, which is a Java representation for just a stream of bytes. You have to be a little careful about how you order it because for some reason Java defaults to using networking style byte buffers, which are and we wrap this in an ONNX tensor. Oh, sorry. I need to go back there. Sorry. We're going to wrap this in an ONNX tensor, which doesn't actually do any copy, just wraps some extra metadata around it and gets the pointer out. Then we run the model by feeding in the tensor along with the name of the input that it is. We get a result object back. That result object we can query to get all of the outputs out. And we can see here that we have 10 values, which represent the likelihood of each of the digits. This is from the MNIST test set, and it turns out CNNs do pretty well at that, which is why one of them has is the most likely and has value 0, score 0. So, as you might expect, if you've done a lot of work with sort of managed runtimes and interacting with native code, basically all of the work here is shuffling memory around between different heaps. In Python, that's a little easier because you can directly access pointers, but the JVM does not let you do that, so it's a bit more tricky. And we want to be as efficient as possible so we can maximize throughput and latency, so to sort of minimize overheads for people. Now, this means that all of our Java objects have to have like a paired native object, and that native object has to be closed, otherwise you end up leaking native memory, and the JVM can't see that because it doesn't know anything about native land. So this is usually done with a try with resources statement, which we saw before. In the future, we're going to look at adding more safety nets to ensure that everything's always cleaned up, even if it's a little bit more expensive to do that cleanup. But that requires newer Java versions. We do actually have paths through this for using regular arrays in Java, but we recommend all users use the byte buffers because, as I said, there's a zero copy path. And you can reuse that buffer again and again, so you don't have to do lots of allocations. But more generally, Java's existing multidimensional arrays are a really bad abstraction for machine learning because they're not flat, and there's lots of pointer chasing, so they tend to slow everything down if you try and use them. So a little bit about where we want to go with this. I think we want to move to a more modern version of Java. Java 8 is 8 years old. There's a lot of new things in the platform that will make working with native code much easier and safer. And there's a bunch of sort of language features that just will make it easier to develop with. We're also interested in adding new features that are coming from ONNX Runtime. So recently there was single op execution support added, and that would be great just to be able to sort of drive a single matrix multiply or some operation that you can't easily get from the JVM. And also there seems to be some work around training, and that would be great to support as well. Training deep learning systems is quite difficult on the JVM at the moment. And we're also going to continue to build out to match the ORTC API as new things added, new execution providers, methods, the extra memory support. Contributions are welcome. This is all done upstream in Microsoft's ONNX Runtime tree, and we'd be happy to talk to you there. Okay, so that was all about inference in models. But it'd be kind of nice if we could actually train models in Java and then export them as ONNX for use in the wider community. You can do this. You can write the protobuf directly, right? You can take the protobuf schema files and emit a Java protobuf object and then write that. But it's quite difficult to write well-formed ONNX models. There's no validation in your protobuf. You can have a perfectly valid protobuf, which is an entirely invalid ONNX model. So we wrote a small open source library for writing ONNX models from Java. We did this for exporting ONNX models from our Java ML library, but there's actually no dependencies on it. It only really depends on protobuf and the ONNX schemas. So you can use this anywhere on the JVM to write out ONNX models. It's Apache 2 licensed. It lives currently in our tree for our library, but we're happy to share this with people if they want to use it. And it gives you sort of attribute validation, checking that your graph is correct. You can easily export Java arrays and a bunch of just sort of nice to haves on top of writing protobufs. So we've got two small examples here. Well, a code example on the right and a little bit of the source code on the left. So we have to define all the operators to mirror them up into Java. So this is a definition of a gem. It takes two inputs and an optional input and produces a single output. And then we list all of the attributes. And because we're doing this, that means that when you build the model, it can validate that the attributes are the right types, that they have the right names, that you didn't supply anything improper, so that you are correctly writing a valid ONNX operation. On the right-hand side, you can see how we write a simple logistic regression graph. So we start by defining some context. Then we define input and output nodes. Then we write out initializers for the weights and the biases of our multi-class logistic regression. Then we do a single gem operation, taking the input, and that emits a gem op. And then we apply a softmax on top of the gem op, and then we assign the output of that softmax to the output placeholder node. And then we can build the graph, and we've generated a fully formed ONNX graph without any circular behavior or invalid operator definitions. So we currently support a subset of ONNX Opset 13 and the ONNX-ML operators. That was basically all the things we needed to export the set of trivial models that we had. We'd like to expand this to cover the full set of ONNX ops. It's really easy to expand the operator enum, and we might actually just look at automatically generating it from the opdef files in C++. That was just a bit out of scope for our initial work. We're at the moment looking at abstracting over opsets to allow users to supply different versions and to use their own custom ops. We didn't do it in the initial version, we hadn't needed it, but it's actually pretty easy to do, and we've got a prototype up and running. And we'd also like to integrate the provenance and metadata into these converted models. We actually export Tribio's sort of very detailed model provenance object with the training data and the hyperparameters in a field in the ONNX metadata, but it's not standardized. We're really interested in the work Intel are doing on standardizing this so that we can emit standard metadata formats. Contributions are welcome to the ONNX export stuff in Tribio, and we're happy to talk about it if you want to.
Thank you so much. Again, if you have questions, go ahead, put them in the chat, and Adam will be there to answer. Next up, we have Ching Len from AWS.
Sure, okay. Thanks for everyone for joining. My name is Qing Lan. I'm one of the software engineer at Amazon Web Services. And today I would like to introduce you with the DeepJL library integration with ONNX Runtime. Basically, we have a few kind of the use cases that are aligning inside of Amazon and also outside of Amazon that have been successful, proving that ONNX Runtime actually have a very good performance. So let's go with the next slides. So firstly, let me introduce what is a DeepJL library. It's one of the machine learning libraries that are built on top of the Java, but more on the application layer. It's actually doing an abstraction of all of the deep learning libraries, just like Keras. And it currently has a set of the NumPy-like operator that we have been implementing inside of Java. And inside of the NumPy-like the operator, we're actually leveraging the deep learning engines that's like Apache MXNet, TensorFlow, and PyTorch by using their C and C++ API to offering the operator support. And also on the engine side, DeepJL library, since it's an abstraction layer, is offer multiple backends. It can run Apache MXNet, TensorFlow, PyTorch, ONNX, PaddlePaddle, and a lot more. And even with even including the machine learning library, just like the XGBoost. We also have a set of the model zoo support with more than 70 pre-trained model that can be run directly within Java, like the popular Hugging Face models, or like the models from the Torch Hub, from the basic image classification to object detection, sentiment analysis, and also action recognition. And the best advantage for DeepJL library itself is basically is service ready. We have been doing a very thorough test run with DeepJL library to ensure it has the best performance and also have a control over the memory. And we have been consistently running, and currently the service has been running with DJL has been successfully for more than half a year with no errors happening. Next slide. Okay. So here I would like to share with you guys about like a couple of the successful customer by leveraging ONNX and also ONNX Runtime by leveraging and also like with DJL used along the way. The first use case is basically came from Amazon advertising. We have been helping with the teams that are trying to launch a model that with a very heavy infrastructure. And basically previously the latency in advertising that does not meet the actual inference goal. Basically, it's like 22 milliseconds. But after using ONNX Runtime, switching from that, it can actually reduce the inference time from 22 milliseconds to less than 15 milliseconds. That's basically the number on the P90. And also, like after switching to ONNX Runtime, we can also providing the thread-safe multi-threading inference by leveraging the multi-core CPUs. On the other side, after doing the conversion between the MXNet to ONNX, we do the correction test to ensure that the output after the conversion is still being the same. And we observe it's less than e⁻⁷ difference on the floating numbers. Similarly, we have the stories that successfully converting from PyTorch to ONNX, which is in the hyperfactor. Since the CDO is here, so I will probably just let him to introduce more. On the other side, we also have the TensorFlow to ONNX conversion successful by using DeepJL libraries. We have Amazon search team here. That is actually, they have old TensorFlow models, and they would really want like a performance boost on their inference side. So after converting to ONNX, the inference time are reduced from 12 milliseconds to less than 4 milliseconds. And since DeepJL library is supporting modular framework, they also converting a couple of their scalar models to ONNX. It also have a very good performance. And finally, it's something that is that wasn't from our expectation. It's actually from the Chinese market, because there's a huge amount of people are actually leveraging PaddlePaddle, and PaddlePaddle is also one of the deep engine that DeepJL library actually support. There are a few of the companies reach out to us to see if there are any performance gain they can get from PaddlePaddle. Because of their original engine doesn't support the thread-safe multi-threading, so they have no way to accelerate the inference by running on the CPU. After converting to ONNX that have the supporting from us, they successfully, like one of the top bank from China, they successfully making their OCR models runtime from 1 second to less than 400 milliseconds on a single image. However, most of the people, especially for people who is using ONNX runtime, they always facing a very big challenge is how, because there's no built-in operators, they cannot easily doing the pre-processing and post-processing inside of Java, especially on the n-dimensional array operation. So DeepJL library offers a solution. So we introduced a new concept called the hybrid engine. And essentially is, in fact, it's just trying to load both two engines together at the same time. And also, it provides a smooth transition for customers, especially when they're trying to switch the engine between, like to run for the inference. So basically, all you need to do is just have a master inference engine. In here, we just use the ONNX runtime and one process engine. In here, we also use the PyTorch in here. And since we're supporting all the operators by using PyTorch, TensorFlow, and MXZ, the user can choose one of the engine to be served as a processing engine. And to reduce the data copying time, instead of like trying to copy the data from Java heap into the C++ layer, we introduce the way by using the direct buffer to send the pointers from the PyTorch directly to ONNX runtime. This avoids the data copying and also providing very huge performance boost on the inference side. If you're trying to comparing, you run the end-to-end inference with PyTorch and this hybrid mode. And finally, the way for us to control the memory management, we're creating something called ND Manager. It's a tree-like architecture that has been implemented in DeepJL library to replace the garbage collection system instead of the Java to provide the more cost-effective memory collection stuff. So basically, having this ND Manager built in mind, we can actually making all the inference very clean without any kind of the memory leaks. Okay, next slide. So here you can actually see how the simple the experience is going to be. So DeepJL library offers us a criteria class where the user can define how their model is going to be loaded. They can offering a model URL. Basically, it can be a file URL. It can be a general HTTP URL. It can even be an S3 link, and also HDFS link. And also, you may need a translator. And the translator is an abstraction class that DeepJL library offers that can be doing for the pre-processing and post-processing. So previously, when the user are actually leveraging the PyTorch, all they do is simply doing the PyTorch in the option engine side, and they load the PyTorch model to run for the inference. And if they want to use the performance boost by running ONNX engine, all they need to do is just convert their model to ONNX, and then without changing a single line of code, just change that engine to ONNX runtime, they can have the performance gain. It's very simple for customers to do the transition, and that's why DeepJL library actually having a lot of customers are leveraging ONNX runtime for their inference optimization. And final slide. Yeah, so what's next with ONNX Runtime and DJL library. So in the next phase, we're going to support for the ARM server because we see there's a training demands for people who are trying to leverage ARM-based device for the cost advantage and also the performance boost. And also we're trying to hit into the edge device, especially like the Android support. We're trying to run the ONNX runtime there as well, and hopefully we will bring the hybrid engine solution to there since we're already supporting the PyTorch inference on the Android device. Yeah, that's it. Thank you.
Thank you so much. Next up, we have hype factors.
Hello, everyone. Am I on? Let's check. Yes.
Yep, we can hear you. And go ahead and take control.
Thank you, Faith. So my name is Viet. I'm the CTO of Hype Factors. And hello from Copenhagen, everyone. We are like a small media intelligence company. But media intelligence, it means, just a moment, where's my slide? Here. Here we go. So what media intelligence means that we are mining the media landscape ongoingly for all various use cases, like product launch tracking and such. And a long time ago, I chose to base our infrastructure around the JVM for the reasons that Adam mentioned in his talk. Also, we find the developer experience very good. This built-in profiler, static typing makes refactoring really nice at large scale. There's a big ecosystem of reusable components. And if you want to make your own, you can do interop to the C4 function interface. And we've built like a whole web crawler around it across 8 million sites. And all our data pipelines are as a consequence built around it. So like how that looks in our infrastructure today is that we get all these different data sources, websites, printed newspapers and magazines, television and radio broadcasts, and social media posts into our system, and we turn that into business solutions like product launch tracking. We track also trust and reputation, or share of voice to see how you are faring compared to your competitors. And there's much more that you can actually mine out of the media landscape because it's like an ongoing information generation engine. Now, under the hood, this is powered by the JVM for the majority of it. And we've been doing that for quite a while. When we were much smaller, it only made sense to enrich this data that we get at these websites and all the articles selectively. We did it with API because it was the fastest way to do it. But then we started to make our own models to customize and to be more spot on with these enrichments. And now we've grown to such a point that we're practically now enriching 50% of our data intake. So we are now migrating to a system that principally enriches all data that comes in. And that leads us to a big engineering problem because we calculated it goes into like a few billion GPU inferences per day. Another thing is that like then our product features are, they're driving on it. So this suddenly like the machine learning and all this model around it are not like nice to have. They become an essential part to keep everything up and running. And therefore the criticality of it increased. So how does it look technically under the hood? We get data in all sorts of formats, HTML, PDFs, and then it goes to pipeline where we use DJL, but it was mentioned by Chin from Amazon, which extracts the ONNX runtime, which also extracts a part of Hugging Face's tokenizers for NLP tokenization. And we use Zyro on top for cooperative multitasking. And that combined together enables us to build a high-performance machine learning pipeline where data is being streamed in, enriched on the fly, and then spit out and put in a database that leads to enrichments like readership, named entity recognition, salience, sentiment, and such. And to run this full scale, we use GPU acceleration. Our initial go-to is usually CPU, simply because it's simpler, and we have had pretty good experience of exploiting the AVX 512 instruction sets to accelerate that. But now we've reached a scale where that didn't suffice anymore. And also to horizontally scale it, we looked at a Kubernetes system to do that. This system was launched last week, so it's running, it's humming right now. It is now yielding at peak load over nearly 1 billion inferences a day. And it was quite a challenge along the way to get it running. First of all, we had to make it economical, so we looked a lot at quantization, which is usually our go-to approach. Initially to 8 bits, but in this case, for this model, we noticed it was we lost too much on the effectiveness of the model. 16 bits seems to be the sweet spot where we got like a 3% gain, 3-time gain over not quantizing it. We also ran into conversion errors, ONNX to PyTorch to ONNX conversion errors. So suddenly, like the ONNX model would yield not a number for the same input, whereas the PyTorch model wouldn't. And we saw that actually happening for specific CUDA drivers as well. So it was a little bit like figuring out what's going on. We figured out it was in the end because of one layer was converted incorrectly. So we decided not to quantize that layer, and that fixed it all for us. On top of that, we invested a lot of the robustness. We added the CI that's GPU powered because we run into this GPU and not a number issues. We decided to make these issues reproducible easily and to alert them when that happened. Another thing was memory leaks. As Chin mentioned, DJL is indeed, I can also speak from my own experience, very robust. And yet we were unfortunate enough to hit like a very rare memory leak in DJL. And it took us a while to hunt it down. We replaced many malloc implementations to profile that. After a while, we figured it out. And it also really happens because we do quite a lot of pre and post processing. So it was triggering quite fast and basically was unsustainable in our production environment. And then, yeah, we had the usual challenge of stitching the drivers match up, and also that it matches up with the container OS drivers. But it's running, we're happy with it. And it's now also served to our clients. And to make sure that it keeps running, we set up a whole Prometheus low-key Provenance stack that monitors like a number of inferences latencies, tokenization latency. To do that, and we will get alerted based on that. And so what we're looking next is increasing GPU efficiency of our system. Right now, we seem to be used around 10 to 20% of the GPU. Not sure exactly how that is measured. So we need to dig into that. But we have managed to push it sometimes to 50%. So maybe it's a matter of, let's say, using a TensorRT engine and loading the ONNX model directly into it. We're also looking to add more models, so that means a multi-GPU setup. And the next thing is to ensure the robustness of the whole system, and we're adding more tests, particularly behavioral testing, which needs to be GPU accelerated because there's quite a lot of that. So that's why our GPU CI infrastructure is set in place. If you have any questions about this particular use case, we are users of the ONNX ecosystem, let me know, reach out to me on LinkedIn or about high factors. I'd be happy to take them. Thank you, everyone.
Thank you so much. So we had a lot of great content already. We are going to break for lunch now. And I want to let you know that actually at 1 p.m., we are going to replay the NVIDIA talk that we had some issues with. So if you want to catch that one, come back at 1 instead of 1:15, and then you'll be able to watch that. But we'll also make it available online after. And then for lunch, it's going to be in the gallery space. So you're going to go out the window, or the windows. Please don't go out the windows. Go out the doors. Go out the doors to the right, get some food, and we'll come back for some more content. Thanks so much. coming through. Yes.
Parameters or Q params. simulating the quantization. Store the final Q params. The goal is to learn the Q params or model parameters which can help to reduce the accuracy drop between the quantized model and the pre-trained model. One of the ways to perform QAT is to use TF-Mod toolkit released by Google. This toolkit implements TF quantization recipe designed for TensorFlow Lite. In this toolkit, quantization is performed using fakequant with min-max vars op, which performs asymmetric quantization. On the other hand, at NVIDIA, we have released a separate toolkit built on top of TF-Mod. This offers features such as quantizing layers by using both layer name and layer class as attributes. We also support pattern-based quantization, and the quantization is performed using quantize and dequantize V2R, which is a symmetric quantization variant. To get the best performance for a QAT model on a GPU using ONNX-TensorRT, we recommend using NVIDIA TF2 quantization toolkit. Here is a quick difference between the NVIDIA's quantization toolkit and TF-Mod. On the left, on the NVIDIA's quantization toolkit, we see the quantization nodes being placed at the inputs of the convolution and weights of the convolution operator. On the right, using TF-Mod toolkit, we see that the quantization nodes are placed at the weights and the outputs of convolution layer. In this slide, we see how we place QDQ nodes according to TensorRT's recommendation, which is implemented by the quantization toolkit. For weighted layers such as convolution or tens, we place QDQ nodes at the inputs and weights of the particular layer. And for non-weighted layers such as concat and pooling, we add QDQ nodes at all the particular inputs. For residual add, we see that the QDQ nodes are being placed on the residual branch of the network. Now, let's look into how we can deploy a model that's trained using NVIDIA TF2 quantization toolkit with ONNX TensorRT. The workflow consists of taking a pre-trained TensorFlow 2.0 model and quantizing it with our NVIDIA toolkit. We fine-tune it for a small number of epochs to simulate the quantization process that occurs during inference and stores the quantized model. We then convert this model into ONNX using TF2 ONNX Converter. Once the ONNX graph is generated, we generate TensorRT engine out of it using TensorRT APIs. In this slide, we see how easy it is to perform quantization-aware training using NVIDIA toolkit by introducing just 4 lines of code. We load the pre-trained checkpoint of the model and use the quantize model function from the toolkit, which transforms the model and introduces QDQ nodes. We then perform fine-tuning of the model for a few epochs and save the final model. Once the fine-tuning is completed, we convert the fine-tuned model into ONNX using TF2 ONNX Converter. TF2 ONNX is a standard way to convert TensorFlow models into ONNX representations. It has conversion support for many standard deep learning operators. We have also added support for converting quantization operators. A quantization operator in TensorFlow is represented by using quantize and dequantize API, which is then converted into 2 separate ops, which are named as quantize linear and dequantize linear in ONNX. Once we have the ONNX graph, we use the ONNX parser in TensorRT, which parses the ONNX model and converts it into an optimized TensorRT engine. The QDQ optimizations and fusions are performed internally, which are then used to build a TensorRT engine. Now, let's look into some accuracy and latency results for recent models. As for the accuracy results, we can see that there is little to no difference between the baseline FP32 and the QAT models across different variants of ResNet. In general, testnets are pretty stable for quantization, which is why the gap between PTQ and QAT is very less. Efficient nets are a good example where QAT preserves accuracy better than PTQ. From the latency aspect, we can see that PTQ and QAT has similar times and introduce more than 10x speedup compared to their FP32 counterparts. PTQ models can sometimes be a bit faster than QAT models since PTQ algorithm only quantizes layers which result in faster model inference, whereas QAT model performance depends on the placement of QDQ nodes and their fusions. So, to summarize, the quantization-aware training provides an alternative to deploy deep neural networks in lower precision. QAT models might be less prone to accuracy drop during inference compared to PTQ models due to model parameters fine-tuning. We demonstrated an end-to-end QAT workflow from TensorFlow to TensorRT deployment via ONNX. TF to ONNX enables converting TensorFlow models into ONNX graphs, which is then optimized by TensorRT. And finally, our experiments with ResNet models showed that INT8 accuracy is on par with FP32 baseline accuracy and that the QAT latency is on par with PTQ. Thank you for attending this session. Hello everyone, I am Dheeraj, a deep learning software engineer.
All right, welcome back, everybody. Hope you had a lovely lunch talking and inspiring about all the cool things you're going to build, right? One thing I wanted to mention too is that there is a survey on. Oh, we're on mute. Okay. Now you ready? Oh, the room is muted. All right. So next up here, we have Ryan. Also, we are putting a survey in the chat. If you could fill it out for the first half of the day, and then we'll have another one at the end. And you also have one in front of you at your seat, if you're in person. Thanks.
Can everybody hear me? Yes, green. Hello? 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 Oh. I seem to have to hold it then. I can use that if that works better.
Make sure you hold it close to your mouth.
Got it. Can everybody hear me? That works? Hello, everyone. My name is Ryan Hill, and I'm a software engineer who has been working on ONNX Runtime since it started about 4 years ago. So what is ONNX Runtime? I figure many of you will already be familiar, but for those who are not, it is a runtime for ONNX models. It is cross-platform, can target multiple CPU architectures for all major platforms, and has language bindings for many current programming languages. Currently, we're doing releases roughly quarterly. Who uses ONNX Runtime? At Microsoft, it's used across all of our major product groups like Windows, Office, Teams, Azure Cognitive Services, and VS Code. We have over 160 models in production with a rough ONNX Runtime is also widely used outside of Microsoft across various industries, with a handful of companies shown here, and a few of which you'll also hear from today. We continue working on improvement with each release and features evolve as new models and scenarios come up from our users. Here are a few notable new features to call out from the last couple of releases. One is that we added new APIs to allow op kernels to be called directly from outside of a model run call so that they can be used like a math library. We had users adding custom ops that extended an existing op, and they would copy the internal code for the op and then add a relatively small change around it. Now they can just call the ops directly. We also added the ability to feed external initializers as byte arrays for model inferencing. This is useful for large models. Previously, this required a file on disk, but now can be done entirely in memory. Performance continues to be one of the key priorities for us, as we support many large-scale, high-volume production workloads. Here are some performance improvements that you get for free just by updating to the latest version. In 1.10, we added a transpose optimizer to push and cancel transpose ops, significantly improving performance for models requiring layout transformation. In investigating some performance numbers, we noticed we could optimize away some heap allocations by doing a small size optimization in our op kernel code to handle shapes, and in related code using shape size standard vector classes. So now instead of using standard vector, we use our optimized tensor shape and inline vector classes. And then, so instead of doing a heap allocation on every instantiation, they're now only done in rare cases involving shapes with larger than normal numbers of dimensions. To give an idea of the improvement, one test showed a drop of 70 heap allocations down to just 6 on each run. And another team saw their performance improve by around 100 microseconds, going from 479 down to 360 microseconds. Quantization has also made some nice improvements. You can see here a bunch of common CNN-based models running up to 50% faster in the latest version. Execution providers are how we enable ONNX Runtime to perform its best on today's various hardware possibilities. Some providers are just ONNX Runtime code implementing kernel ops using a hardware API, like CUDA, and others are using a software library that already implements the op math optimally using a particular hardware API, like the TensorRT library, which uses CUDA, and OpenVINO using various Intel hardware. So why not just use a library like TensorRT directly? Well, for running models, ONNX Runtime offers a single API that gives you the flexibility to run on almost any target hardware optimally with very low overhead. And ONNX Runtime has a complete CPU implementation. So if something isn't supported in a provider, it will fall back to the CPU version. In developing these providers, our engineers work together with the outside company engineers to ensure the best results and to create an ongoing relationship where everyone benefits. As you can see, as these hardware APIs and libraries continue to be updated, we continue to update our providers along with them to ensure that we maintain top performance and the latest hardware support. We saw the need for a performant, low-footprint model inferencing solution on mobile devices and released the ONNX Runtime mobile packages about a year ago. Since then, we've continued to invest in these platforms to improve usability for mobile developers, like how we can now do NHWC conversion at runtime, which is not mobile specific, but we ran into this on mobile. It's used when you have a kernel implementation that prefers a specific layout, for example, running on ARM or using NNAPI. The converter is aware of the layout-sensitive operators and can replace nodes using them with an NHWC version. Internally, it does this by wrapping the appropriate nodes with transpose operators, and then, thanks to our transpose optimizer, it then removes any transposes that effectively cancel each other out. We tested this using a production model that uses our new XNN pack support, which uses NHWC, and the input was also NHWC since the model came from TensorFlow, and all of the added transpose ops canceled out, including the initial input transpose. Ideally, this is what typically happens. For C# users, they can use ONNX Runtime in cross-platform apps, including apps targeting Android and iOS. We currently support Xamarin and are adding .NET 6 MAUI support in the next release. Fingers crossed. this will be a very interesting thing for C# developers on mobile platforms. We also added Android and iOS packages with the full ONNX runtime builds. This will make it simpler for users getting started using ONNX runtime in mobile scenarios. They can use ONNX models, and all offsets operators types that ONNX runtime supports are included. It has a larger binary size, but this probably isn't an issue for most users as it's still relatively small. To give an idea, a minimal build that only includes necessary ops might be around 2.5 megabytes, and the full build is around 8 megabytes. ONNX Runtime Web is one of our newest offerings as we've seen growing interest in directly running inferences in the browser. We used to have a side project called ONNX.js, but this wasn't ideal. We needed to maintain two separate versions of the code, a JavaScript one and the primary C++ one, and we needed to ensure that the behavior was identical. Now we just compile the main C++ code into WebAssembly so that the ONNX Runtime Web is backed by the same core code base. As a bonus, it's faster, it uses less memory, and the resulting binary is smaller, basically like having another target architecture to compile for. Another big achievement for all of our JavaScript users is that we introduced a JavaScript library called ONNX Runtime Common, which has multiple backend implementations, Web, Node.js, and React Native, but one single common API. This allows the same JavaScript code to run on all the main web platforms. We also added X and NPAC library support, and if the performance is good enough, we'll have OpenGL support in the upcoming 1.12 release. Challenges with data pre- and post-processing has been a recurring hurdle. We also recognize that custom operators used with ONNX Runtime that weren't officially in the ONNX spec could be shared. This led us to create ONNX Runtime Extensions, which is a library of shareable custom ops that can be built and run with the core ONNX Runtime operators. These are currently focused on model pre-post-processing work. The user no longer has to implement this in an outside language. It can be done entirely inside the model run call. It has things like text conversions, for example, changing strings into uppercase, lowercase, math functions like splitting positive and negative values into separate tensors, etc. Currently, the ops in the library are mainly focused on NLP, natural language processing, vision, and text domains, which present some of the most challenging data processing steps. But we expect this to evolve as new needs are identified. There are flexible build options for it, like having it be a part of the ONNX Runtime library through the static library build option. It's currently being used by our internal partners in the Microsoft Office team. Community. Thank you. That's it.
You're good. Thank you so much. Next up, we have Jeff from Hugging Face. Come on down.
Hey. Can everybody hear me with this one, or should I use that one? Hey, is that good? There we go. Can you guys hear me? Sure. Is there a volume button on there? Should not do that.
No, it's a different channel. Do you want to try this one?
I can use the.
You want to use the
thing
handheld?
and
Okay.
to switch up the slide.
Right here. They'll just make sure you speak into it. If you hold it down here, you won't. So like speak.
And
Hi. All right, I'm here. Hi, I'm Jeff Whittier from Hugging Face. I'm on the product team over there. I'm super happy to be here. Thank you so much, Prasant Kassi, for inviting me to talk to you today. What I want to talk about is how you using the Optimum library and its integration with ONNX Runtime. So all the goodness that Ryan was just telling you about is available to easily be applied onto transformers models using the Optimum library. All right, so let's get started. It's a short talk, and I'm going to breeze through everything. So if you have questions and we don't have time to ask questions, don't hesitate to ask me directly. I'm at jeff@huggingface.co. Through this talk, I'm first going to take a step back and bring you into the transformers world and how we got to where we are today, to then talk about Optimum, why we went out to build this specific library that's focused on accelerating transformers models. But first up, a little bit of a trivia quiz. So what do Tesla, Gmail, Facebook, and Bing all have in common? The answer, you know it, it's transformers. But the point that I'm trying to make is that there are very few companies in the world that are able to make billions of predictions based on transformers models a day, which Gmail is doing through its autocomplete, which Tesla Autopilot is doing. And same goes for translation on Facebook or search results with Bing. So what are we trying to do at Hugging Face? Well, we're trying to make the power of those transformers models accessible to every single company in the world through readily accessible pre-trained models and through tools to make use of it all. For us, the initial conception starts with the advent of transfer learning, of the attention is all you need paper. This is what really changed the field of machine learning. It changed the field of machine learning first with NLP by achieving breakthrough performance in every single natural language processing task. But it is today producing state-of-the-art results in every single modality of machine learning. And I think that's the first time throughout the history of machine learning that every single community, the speech community, the vision community, the NLP community, the reinforcement learning community, chemistry, healthcare, everybody is working with the same set of architectures with slight variations, and everybody is working from the same set of tools and speaking the same language. So it's really been a privilege for Hugging Face to be at the center of this ecosystem, to be the home for the community that is sharing and improving upon what is possible. Greater than what you would expect from a team of now 150 people. We really represent the aggregate contribution of over 1,300 open source contributors to our libraries. And of course, we provide access to over 50,000 fine-tuned pre-trained models for every single machine learning task you can imagine, for every single language you can imagine, all contributed to by our community. And that focus on a community, on collaboration, on making machine learning open and collaborative has really fueled our traction. Today, Transformers is the reference toolkit to make practical use of attention-based mechanism of Transformers models in every modality. And so now Optimum. Why Optimum? Well, whenever I talk about the history of Hugging Face, I show this graph, which is very a prehistoric graph, and by that I mean it predates GPT-3. But even by then, the trend was really clear, which was this exponential increase in the number of parameters of models that make it more challenging for engineers, for machine learning engineers, for software engineers to make use of those models in a production context because they're getting hungrier in terms of compute resource, memory resource, bandwidth resources, and it creates a whole struggle for infrastructure teams to make use of these models. And that's why we decided to create a specific library, Optimum, that is focused on the acceleration of transformers models from training to inference. Because if you want to reduce the latency you get from a vanilla PyTorch TensorFlow model to something that you can use for real-time use cases, to something that you can use in a cost-effective way, you need to decrease the latency through 3 different layers of complexity. You need to work on your model, editing the graph. You need to work on accelerating the inference, and then you need to work on like the hardware-specific optimizations to get it all down to millisecond levels. So Optimum is that bridge. It's the bridge between the transformers library and the hardware and hardware peak performance. In the same way that with transformers, we made transformers accessible by offering a high level of abstraction and easy to use APIs, we want to do the same thing for hardware acceleration. And so with Optimum, we want to offer the reference toolkit for hardware acceleration, offering these high-level APIs dedicated to production performance. So today, Hugging Face Optimum is this one library through which you can get peak performance leveraging these acceleration libraries and solutions from our partners, ONNX Runtime, Intel, GraphCore, Habana, all within the Optimum package. So let's focus on the ONNX Runtime package within Optimum. We can already today use Optimum to accelerate your trainings of transformer models in a very easy way, to accelerate the inference of your transformers models in a very easy way. For training, we introduced a new trainer class called ORT Trainer. And if you're familiar with the transformers library, you're familiar with the trainer library. And it's really an easy 2 lines of code switch to go from your transformer trainer to the ORT trainer to take advantage of all the acceleration that it provides. One of the main benefits is that through the ORT trainer, you get native integration of deep speed, and that produces amazing acceleration results. In fact, I'm sharing here some preliminary figures shared by Ashwini Kad at Microsoft, benchmarking Optimum ONNX Runtime, and showing that you very easily get, through these very few lines of code changes, 10 to 40% acceleration in the throughput of your training, depending on the configuration, which stage of this deep speed you're going to be using. So it's really powerful, but very simple. Then if we want to talk about inference, there are 3 main classes that I want to talk to you about. Like the first one is ORT Optimizer. It's a simple way to simplify the graph from your model. You can simplify the graph from your model by specifying just the pre-trained model and the task. And what you get is a set of basic optimization, like constant folding, like operator fusion, that are going to be applied across the board. And you also get advanced optimization that is specific to the execution provider that you are targeting, whether CPU or CUDA. Once you have an optimized graph, you can optimize the weights. You can optimize the weights by quantizing the model, and you can do so very easily using the new ORT Quantizer class. And with the ORT Quantizer class, you have access to both dynamic quantization and static quantization. It's a simple parameter change to go from one to the other to get state-of-the-art acceleration. And you can do so by targeting the specific execution provider that you're going to be using to take advantage of those hardware-specific optimizations. And last, if you're familiar with Transformer, you're familiar with the auto model for task classes, which is how you're able to very easily apply a model to a specific machine learning class. Well, with Optimum, you can do the same for ONNX Runtime and benefit from all the hardware acceleration by switching your auto model for task to ORT model for task class. And so again, it's like a very easy change to make to benefit from all the optimizations that ONNX Runtime provides. And something that I'm super excited about and that the community is super excited about is that we're collaborating together to enable sequence-to-sequence model optimization through these Optimum Accelerated Inference Pipeline classes. All right. So to put it all into like an end-to-end example, we just published a new blog post you can find on our blog at hf.co/blog. It's called Optimum Inference. And in here you have the whole sort of user story, starting from a pre-trained model that is fine-tuned for QA, and then exporting it to ONNX, applying the optimization, applying the quantization, and using the ORT model for QA class to get accelerated performance. Here, getting 44% throughput increase or latency decrease while conserving 99.6% of the original model accuracy. So that was what I wanted to talk to you about. I invite you to check out and give a start to the Optimum library. It's on our GitHub at GitHub Hugging Face Optimum. Thank you so much.
Next up, we have Bowen from Microsoft.
Hello guys, I'm Bowen and I'm a software engineer working on the PyTorch-ONNX Converter at Microsoft. So today I'm going to give a briefly overview of the converter, basically what it is, what it does, how it does it, some interesting features, and the future roadmap. Okay, so here's the brief overview of the architecture and flow of the converter. So I think throughout the talk, I will use the word export and convert interchangeably. The converter lives inside PyTorch. It's part of the PyTorch package. Its source code is in the PyTorch repository under GitHub. So to start, you have a PyTorch model. You have some sample input, and together you pass it to the Torch-ONNX export API. The first step, we utilize the Torch tracer and Torch script to convert the PyTorch model to the Torch intermediate representation, or what we call Torch IR. So the second step, the exporter takes the Torch IR and through various passes and graph optimizations, convert it to ONNX IR. And as a final step, it serializes it to the ONNX model in a protobuf file. So yeah, in this talk, I'll try to not get into every tiny bit of detail. However, in the footnote, there's always links to more information and documents. So yeah, feel free to check it out if you're interested in certain topics. Okay, so let's start with a very simple and basic example of, so this is how it looks like to export an AlexNet. A single call to the export API, and you can use the Neutron tool to visualize the ONNX model. So the arguments in the box are optional, but you can provide them if you want to export your model with dynamic input and output shapes. Okay, so let's move on to some of the interesting features of the converter. So first is quantization. Recently, we added support for exporting a quantized model. The quantized operators will be exported in QDQ format. So if like supported by backend, it can be fused and run as a quantized operator at runtime. People can write models with the Python control flow, the loops and ifs, and these are captured in ONNX model as the ONNX loop and ONNX if nodes, together with a composition of other nodes as their subgraph. So one of such example is the export of the autoregressive transformer model. It can capture the entire beam search and or like a greedy search algorithm inside a single model. And of course, there's other ways to do that. For instance, if in some cases you might already have a specified kernel in your favorite backend, and in this case, you might want to capture a subgraph of the PyTorch model as a single ONNX node in the ONNX model. So this is when like the custom ops come in. There are various ways to export as custom ops. You can write a custom torch autograph function and define the forward and backward routine in the static method, forward and backward, respectively. There is additional static method symbolic, which basically tells the exporter how this custom function should look like in the exported ONNX graph. Another scenario would be that you already have a pretty well-defined PyTorch operator, be it a custom PyTorch operator or a standard PyTorch operator that somehow the exporter has not yet supported. So in this case, you can utilize this API to register a custom symbolic function. So to tell like exporter basically how to export it. And of course, you can write it as either exported as standard ONNX ops or like any custom ops in custom domain. So next, I want to talk about ONNX local function. I want to first introduce a little bit of the background and motivation. A lot of times, the common complaints we receive is, for the exported ONNX model is that the nodes are all flattened. So in a sense, it does not like reflect the hierarchical relationship between layers and modules. So for instance, for this LIR norm, since I think back then it was not a standard ONNX op, it was exported as a composition of different nodes, and they are in some way sort of like flattened, mixed up with other nodes in the ONNX model. So this makes it like visually hard to figure out what was what back in the PyTorch model, and it also it's kind of hard sometimes for backend to do fusion and optimization. So what this local function feature does is that now it allows you to specify a certain torch NM module class or this node has type function, and the previously seen subgraph or the composition of ops now are stored as the function body inside the ONNX model locally. So this provides a means for backend to still be able to run this node or model without like having a specified kernel. Okay, mixed precision. So yeah, we support both Torch AutoCast and NVIDIA Apex MP. There's no really like extra step needed. You can export the decorated model as how you would with any regular model, and you would have the cast nodes inserted. Okay, so let's talk about and diagnosing failures. So we want to improve that experience, and we want to provide more tools to help make that process easier. And of course, we will keep on focusing the support of more and more models export out of the box. Okay, so to wrap up, these are a handful of useful links. There are links to documents of different components. There are links to useful tools, and link to a place where you can file issue that is related to Exporter. So thank you all for tuning in, and I hope this talk is helpful or interesting.
Thank you so much. Oh, now we have volume. I don't have to hold it so close. Okay. Next up, we have SAS. They are a virtual recorded call, so if you are on the Teams meeting, you might have to hit play on the video if it doesn't play automatically.
Today we are going to discover how we solve a customer issue to detect safety-and-sound violation in their factory, and we achieve this using the ONNX models and a tool from SAS called SAS Event Stream Processing. What we would like to achieve for this customer is they're using their existing camera, in this particular scenario we're 12, to detect if one of their employees was entering some dangerous area where machinery was moving, and in such scenario provide an alert. The key focus area for this engagement was the ability to detect people using an open source model from ONNX Model Zoo, and deploy this in production using multiple cameras. We stated it was 12, but could be more in the future. We are discussing for expand this to additional factory, where will be up to 40 cameras for each factory. And this need also to be integrated along with the downstream system of the customer to process and send the alert violation, but also to monitor the health of the system, ensure it's up and running, and eventually notify the customer about issues, for example, broken camera, that allow them to repair promptly. This solution was achieved thanks to one of the SAS tools called SAS Event Stream Processing. SAS Event Stream Processing is part of the complex event processor family, so it's a tool able to analyze in real time millions of events per second, and achieve so by using a publish-subscribe interface. The data in streaming come to the publisher interface, are elaborated by the tool, apply some algorithm. In this scenario, we apply computer vision algorithm, but also geofence algorithm to ensure that the people were or not in the wrong position. And then, once we have a result, we publish this result to another source. This tool is also engineered for agility, so has a very small footprint that allow him to run in the smallest device, like Raspberry or NVIDIA Jetson, but also scale to biggest system like cloud or big edge solution, like in this scenario. This tool could be accessed, it could be developed using online graphical studio, SAS ESP Studio, that allow you to draw the flow of the data, and apply all the transformation needed to fulfill the requirement of the algorithm you need to run. It's also possible to create a run model in a standard Jupyter notebook that is usually used by data scientists. Once you develop the model and you are ready, then you could use another tool called SAS Event Stream Manager to place this in production and monitor the status of this project. What we did together with Microsoft is integrate the ONNX Runtime inside of Event Stream Processing, allowing the customer to access the capability using the standard interface and the other facility from SAS Event Stream Processing. To integrate this, we allow to achieve from our customer to get the ONNX model on their favorite frameworks. That could be also SAS. We also have framework called Visual Data Mining and Machine Learning that is supported in ONNX, but also from CAFI, PyTorch, common machine learning frameworks. This ONNX model then is processed, is attached to an ESP Studio model that allows them to transform, for example, to modify the picture that is coming to the flow in a format suitable for the model. And then the model, along with the project, is shipped to the ESP server that, thanks to a plugin we developed, could use the facility to the ONNX runtime, and then also leverage the execution provider for the hardware acceleration. The beauty of our solution is that we ship all together in a Docker container, including the driver from CUDA or TensorRT, including OpenVINO to run on CPU. What proposal we suggest to our customers? Since they have this requirement of ensure that they detect violation and to be resilient, we suggest them to a modular solution that split the activity needed for process this image in several steps. And each step then is using Kafka as a buffer queue to ensure that if something goes wrong in one of the processing, the full flow, the full pipeline is not harmed. We could just keep the data in the Kafka, and then when one of the processes is restored, we are able to continue the flow. The first step, of course, is acquiring image from cameras. I will see that we have one step for each camera to ensure that if there is one problem, not all cameras are affected. Then we have a model that processes the computer vision and level a GPU that user has scarce. So we condense in this model all the requirement for computer vision processing, and then we have another model that is responsible for post-processing. To see this in the real deployment, we have this image. So, important to note, we deployed this with what we call workload in the edge in a Kubernetes cluster. So it's a more bigger edge that we used to, but still an edge solution that's use Kubernetes as a deployment mechanism. And then we also have, of course, we connected with a centralized cloud solution to monitor this cluster, and in the future to monitor more cluster that will be more factory from a central location. In the workload inside at the edge, as you see, the step one is the ingest the video. And we have one pod inside the Kubernetes for each camera to ensure that nothing could happen. The camera cannot harm the other camera. There's no possibility that we lost more than the camera that at the moment are not really working. All this ingest video is placed on a Kafka bus and then processed by another pod that's running ESP that's processing and read the image from Kafka and create the result of the computer, publish the result of computer vision model. This pod, the number 3, is complemented. This is optional, but it's usually important by some additional sensor data from the customer that allow us to understand if the equipment that we are recording in the video of that particular camera are active or not. This, of course, is important because it's usual that people will go to the field to repair machine where I stopped. It is allowed, it is not an alert. But of course, this is completely different if the machine is running. In this case, we need to enforce the rule and send an alert in case the people enter in the space. So we say that the pod, the process 3, she will send back the data to Kafka bus, of course. Possible to check along with a database of location in each camera. Each camera could have multiple locations that are dangerous, and of course we have multiple cameras, so we have a database that registers all the dangerous location, and we read this database and we determine if the coordinate of the person we detected on the step 3 are inside or outside this area. If outside, we write out an alert that is then processed by the step 5 that is responsible to save the image to a solution, could be SharePoint or another report in CV. And then we have the step 6 that send to the system the alert along with the path of the image with the violation. This process is complemented with some heartbeat solution to check all pods are running, and also a process fault solution that ensures that if something wrong, for example, if a camera doesn't work, we automatically inform the app system. Worth to mention that this architecture is currently in production at one of our customer facilities, and we are currently working to expand this to more than 20 plants in the coming months. This slide highlights the key benefit of this solution from our customer perspective. The ONNX Runtime integration ensures an optimal time to value, thanks to publicly available pre-trained models and the reuse of customer assets. This permitted us to reduce the overall project timing to less than a month. The architecture resiliency was another key benefit, and this was ensured thanks to Kubernetes and Kafka. Performance and scalability, especially, are other fundamental aspects of this architecture. Having centralized the usage of GPU to a single pipeline module ensures an efficiency in hardware acceleration and also enables scalability by allowing to increase the number of GPU when needed. Finally, the solution allows to increase the number of cameras easily and provide support for different kinds of post-processing analysis beyond the fence used in this scenario. As an example, we could introduce a logic that counts the number of people in an area to avoid crowds, or we could verify that a machinery is not performing dangerous actions. This is all I have for today. Thanks a lot for listening, and feel free to reach us for any question at the address shown in this slide. Good morning. My name is Daniele Cazzari, and I will be your
Thank you so much. Next up, we have Felix, or no, wrong one. Sorry, we have Matthew at Bizarre Voice.
Hi everyone watching live at the Microsoft Silicon Valley campus and watching virtually as well. The single biggest change in the shopping experience in recent years is the digitization of commerce. Brands and retailers have gone from fighting over limited shelf space in physical stores to fighting over the infinite shelf space across the internet. Standing out amongst the crowd is now harder than ever. One advantage e-commerce companies possess is the scale of data they have and collect. Creating impactful insights using AI can be the differentiator between winning and losing. Today we're going to explore how to tackle big data problems with lightweight solutions with the help of ONNX. Before we get into that, a little bit about myself. I've been fortunate enough to work with a range of innovative tech for several years now. I'm currently a software engineer at Bizarre Voice, and over the past year or so, I've been focused on harnessing AI to improve the online shopping experience by delivering e-commerce machine learning solutions to the cloud. So let me try to illustrate the scale of data in e-commerce and why the application of AI is so compelling by using Bizarre Voice as an example. Bizarre Voice manage and process data for over 1 billion shoppers a month. They have the world's largest network of brands and retailers, and they provide over 8 billion total reviews for these brands and retailers. The variety and data and scale of data here would cause any data scientist's mouth to water. It's obvious there's massive opportunity here to innovate in this sector using AI. It's the reviews I want to focus on today specifically. The Bizarre Voice network allows brands and retailers to share product reviews across catalogs, meaning one review on one site can be shared to every place that product is sold online. More reviews equals more consumer trust, which ultimately equals more sales. The process of sharing reviews is called review syndication, but this is a topic for another day. We want to explore the concept of sharing reviews today, and that concept is powered by product matching. Product matching is the process of determining if two products are the same. It's the core function of the machine learning model we built. Product matching is performed by comparing unique product identifiers, but whatever is left over and can't be unmatched is done manually, or in other words by humans. In fact, over 1 million product matches a month or performed manually. You can imagine how tedious this can get and expensive as well. But how do humans product match if we take a step back? Well, if we take a look at these two products on screen now, how can we tell they're both the same? Well, we look at the picture, we read the text, price, ratings, reviews, the description, and gather enough data to come to an accurate conclusion. And subconsciously, we're carrying out techniques that machines use to solve this problem: numerical processing, text processing, and image recognition. And these are the basis of how we built our model. And of course, we need data. We gathered a data set of over 3 million historical product matching human decisions to train our model to a 99% precision rate. So that's the first part of our solution, the model. A scikit-learn model built with Python, exported to ONNX format. Now that's all well and good, but how do we implement this into our services to generate real business value? Well, let's now look at approaches to deploying machine learning solutions to the cloud. For me, the ideal solution is an implementation that is the most lightweight, cost-efficient solution that also maintains performance. With that in mind, these points here in this slide are based on results I've personally seen in the past. On the y-axis is complexity, on the x-axis is cost from high to low. First of all, we started looking at virtual servers like Azure Virtual Machine or AWS EC2s. This can give you the most flexibility as you have an actual OS to work from, but comes with some unnecessary configuration and costs, especially if you're using it specifically for machine learning. I'll touch a bit on costs later, but why overcomplicate things when we don't have to? The next consideration is a cloud ML platform like Azure Machine Learning or AWS SageMaker. We now have the benefit of dedicated ML tools at a lower cost in some cases than a virtual machine. But we must remember at this stage, it may be the case that the machine learning engineer hands over the model to an engineering team to implement. And personally, I want a development pipeline that software engineers who don't specialize in machine learning can pick up and use seamlessly. So that's when we arrived at a third option, serverless functions. Now, like Azure Cloud Functions or AWS Lambdas, these remove the overhead of managing servers, configuring software, and patching operating systems, and they're also very cheap. So this is the option we explored. And this is the solution we came up with. So we developed a scikit-learn model, exported it to ONNX format, and built it with Python, deployed it to a serverless function, and we used a node environment to run inference on ONNX Runtime. ONNX gave us the flexibility to be able to build a model in Python and deploy it to whatever environment we wanted. And we chose Node because that was based on similar approaches we've chosen in the past, so it really worked well for us. And by running this, we can send predictions out to our network. And just by using this lightweight solution, we were able to process hundreds of millions of pending product matches within the timeout limits and deployment size limits that are part and parcel of serverless functions. What's also great about this solution is the modularity of it. We can plug this in anywhere to any of our services quickly and easily. But how do we scale this solution to hundreds of millions of predictions? Well, if we look at this table, this is based on results I've seen in the past with machine learning inference on serverless functions using ONNX Runtime. These metrics help us find the optimum memory size to avoid timeouts and ensure the best performance while keeping costs low. I like to use the metrics memory used and execution time. If the memory used nears the total allocated memory, or the execution time nears the timeout limit, we know we need to scale higher. This is an instant indication that we need to scale. If we look down the left at allocated memory, we can see that at 4 GB, performance plateaus, and therefore 2 GB is the ideal memory size for for us as it stays within the memory usage and easily within the timeout limits, and is also the lowest cost there at $2,800. Now if we compare this same model with the same compute loads across serverless functions, cloud ML platforms and virtual servers, we can get a great grasp of the cost savings here. You can see that serverless functions is significantly cheaper in our case than the cloud ML platform, and significantly again cheaper than a virtual server. So there's great cost saving potentials here by using this lightweight approach. One consideration I'd like to bring up is that Python packages add up very quickly. We can see by this chart that the orange and blue line donate deployment size limits of serverless functions, and that popular machine learning frameworks like TensorFlow and PyTorch already exceed these limits. And that's even before we add any logic to our serverless function. ONNX helps us reduce the size of our models during deployment, but sometimes our deployment sizes are too big. There also are workarounds around this, like fetching our model from a different cloud storage source into our serverless function. But again, ONNX helps us reduce the size of these deployments. So the two main considerations to these approaches is the deployment size limits and working within the timeout limits. But I hope this demonstrates the power of ONNX and ONNX Runtime when deployed to a serverless function. Using this lightweight approach, we are able to match hundreds of millions of products across thousands of client catalogs at high speeds, resulting in over 15 million extra reviews for brands and retailers, proving that this approach is fit to process data on a grand scale. So we've explored just one way of utilizing the capabilities of ONNX and ONNX Runtime. If you want to hear more or want to share your use case with me, please reach out. I'd love to hear it. And as someone actively working in this space, I'm both intrigued and compelled by where these technologies are taking us. Thank you.
Thank you so much, Matthew. Next up, we have Nikhil from Adobe.
Hi everyone watching live at the Microsoft Silicon Valley.
Hi everyone, today we're going to talk about high-performance machine learning for video and audio. My name is Nikhil Kalra, and I'm a senior software engineer at Adobe working on the applied machine learning team for video and audio. Some of the products that my team works on include Premiere Pro, After Effects, Audition, and Character Animator. The machine learning workflows that we develop revolve around one central concept. We want to enable creators to spend more time on the edit and more time in the creative process than they spend in redundant and repetitive workflows. Some of the features that we've worked on include auto reframe, scene edit detection, auto color, auto captions, and transcription. So, what makes video workflows unique? The first is that they're inherently resource limited. The CPU and GPU can currently power decode, render, encode, and machine learning inference. Our biggest bottleneck is transfer. That's PCI bus saturation on discrete cards and memory bus saturation on integrated cards. Our workflows are extremely data intensive. Common formats that our customers use include 4K at 60 frames per second or 8K at 30 frames per second. That's 6 gigabytes a second of uncompressed footage. And the third is that our workflows are compute heavy. Not necessarily in terms of GPU compute, but at minimum, every machine learning workflow requires the render pipeline to spin up to either resize or relay out a frame from a packed to planar format. That brings us over to our overall video processing pipeline for machine learning. First, we'll read the compressed or encoded media from disk and hand it off to our decode pipeline. If the media is in a format that we have hardware decode support for, we'll hand it off to the GPU or dedicated hardware decoder. If not, we'll fall back to the CPU and perform the decode in software. Next, we'll move on to the render portion of our pipeline, where we'll use a combination of GPU and CPU rendering in order to produce a frame for our machine learning engine. Finally, we move on to the machine learning portion of our pipeline, where we take that frame and run it through our inference pipeline, running on both the GPU and the CPU. So all of these different pipelines means that Premiere ends up having a lot of concurrent GPU activity running in the background on various different technologies. On the hardware decode side, we use a lot of vendor-specific frameworks, such as NVDEC, the Intel Media SDK, and the AMD Media SDK. On the render front, we use CUDA on NVIDIA GPUs and OpenCL on AMD and Intel GPUs. And for machine learning, we use DirectX and DirectML to back our pipeline. All this to say, our biggest bottleneck is transfer cost, going off of the GPU and off of the hardware into CPU memory so that all of these pipelines can work in parallel on the different underlying technologies. So we use the ONNX runtime to power all of our machine learning workflows on Windows and a handful of our workflows on Mac. And we use the DirectML execution provider for GPU acceleration on Windows platforms. On Windows, the Creative Cloud apps target the entire Windows ecosystem as a single platform. This means two things. One, that we must provide feature parity across all major IHVs that support Windows, NVIDIA, Intel, and AMD being the big ones. But two, we must also provide functional parity across equivalent hardware from different IHVs. In other words, our customers expect that equivalently classed NVIDIA hardware performs the same as equivalently classed AMD hardware, even though they may be using two different GPU technologies under the hood. As a result, we chose the DirectML execution provider as our way to deploy ONNX models on all hardware in a common runtime versus adopting the individual vendor-specific frameworks such as cuDNN, OpenVINO, and AMD's MLIR-based. Our main motivation here was performance. DirectML internally uses meta commands to enable the use of vendor-specific hardware, such as tensor cores on NVIDIA GPUs. And that's especially important for us because it leaves hardware free for other async compute workflows, including render and decode, that may be occurring simultaneously in the background. On the performance front, the ONNX runtime has had a few historical bottlenecks that have greatly impacted our workflows. The first is that there was no GPU input support. At minimum, we were required to perform a GPU to CPU readback in order to pass a frame buffer into the ONNX runtime for inference. The second is that batched workflows inside of the ONNX runtime require a contiguous memory buffer, which forces us to make additional memory copies as we copy from the locations in which our frames were decoded or rendered into this contiguous buffer for inference. Now, with newer releases of ORT and the DirectML execution provider, we have a path forward for enabling performant workflows that don't exhibit these same bottlenecks. New bindings with DML enable us to pass GPU frames as inputs into the inference pipeline, meaning that we can use CUDA and OpenCL to DirectX 12 interop in order to create these DML resources. At the same time, we can now assemble batches asynchronously on the GPU using DirectX 12 copy queues, which one, increases the available bus bandwidth for the application because we're able to control the copy, but two, it also decreases the latency that we experience in our inference pipeline by allowing us to experience that transfer cost asynchronously. Additionally, and this is more forward-looking, I/O binding support with DML will enable us to use output buffers and directly consume them in a DX12-based pipeline, enabling the use of machine learning-based models for GPU workflows. We also hope to use I/O bindings with DML outputs in order to reduce the latency that we experience on the output side of our inference pipeline by performing CPU readbacks, if necessary, asynchronously using DX12 copy queues. So we've also made additional performance optimizations by building a framework on top of the ONNX runtime to allow efficient interop with everything else that we're running in the application. For us, that means that render and decode always have the highest priority because we need to produce frames for the inference engine. And we back off of inference whenever the GPU is busy or starved for resources, for example, if we're in a low GPU memory situation. And this is increasingly common as our customers gravitate to using higher frame rate and higher resolution media for their workflows. The third is that we also try to assemble our inference requests into batched workflows to reduce resource contention with the GPU and minimize driver overhead. This is what that looks like in practice. By dispatching inference requests sequentially, we incur GPU driver overhead not only on the input side, but also on the output side, and then we incur that repeatedly over the size of our entire inference pool. On the other hand, by switching to a batched workflow, we're able to amortize the cost of GPU driver overhead over the size of the entire batch. But more importantly, we're also able to delay the execution of our inference request until we've assembled this batch, meaning that we can leave the GPU free for other work that's also incurring, such as render and decode. Let's take a look at scene edit detection, for example. This workflow requires us to decode and render every single frame in a clip, and then run each of those frames through a network to determine if there is a cut between two frames. Scene edit detection is an extremely resource-intensive workflow. For a 1-minute 4K clip at 60 frames per second, we dispatch about 3,600 inference requests to the engine on a total of 6 gigabytes of video data. We're able to run that entire pipeline end-to-end from decode to inference in about 10 seconds or 6 times real time on modern high-end GPUs. None of this would have been possible without the performance enablements provided by ORT and the DirectML execution provider. So looking forward, there are a few more changes that we'd like to make. First, we want to leverage the ONNX runtime to enable machine learning-based workflows during GPU render. And as more of our GPU compute transitions to DX12, this will become even easier, because we can minimize the cost by removing the overhead that's currently associated with OpenCL and CUDA to DX12 interop. But more importantly, we want to transition our pipeline to look more like the pipeline on the right, where we can keep as much stuff on the GPU or GPU addressable hardware as much as possible and minimize our transfers to the CPU unless absolutely necessary or are required for any user-facing features. That's all I have for today. Thanks for watching.
Thank you so much, Adobe. Next, we have Alexander. He is presenting live from Topaz Labs. Alexander, can you hear me? We can't hear you. Why don't we take a quick 5-minute break while we get Alexander connected? We have some snacks that were just set out in the back of the room as well. So grab some snacks and we will be right back.
Oh, I'm sorry.
There you are.
Sorry, I did not realize I was muted.
No worries. We're just going to take a quick 5-minute break and then we'll start with your presentation, okay?
Yes, that's fine. Thanks.
Thank you. All right, we are going to get started again here with Alexander. If you could take control of the presentation, we are ready for you to go.
Yeah, thank you. I'm Alexander Zhang. I'm a software developer at Topaz Labs, which is what could be described as an image quality company. Gigapixel is the product of ours I've worked on the most. It's a desktop app that lets people with no knowledge of AI or programming use super sampling models to enlarge, say, old photos to the size needed for a poster. A critical part of accomplishing our goals is to fit into an existing workflow. And that means apps and plugins that run on the user's desktop or laptop. And it means getting the performance users expect out of whatever hardware they have without manual configuration, and keeping up with advances in the state of the art by delivering the latest and highest quality image models available at any given time. Desktop is a somewhat less common deployment scenario with many of its own challenges. It allows users to edit offline and not worry about internet speed or privacy policies. But when compared to a server deployment, there's a lot less control for us over the system. Restrictions on the GPU or operating system have to be carefully considered, and while we can provide a set of system requirements, it has to be reasonably broad and easy for users to check. There's also more diversity in desktop GPUs than even most mobile or embedded deployments, and users expect not only to be able to run everything with more than 5-year-old cards and drivers, but also for the performance to scale well on the latest hardware. There's also usually other applications running, like photo editing software, which can put memory or responsiveness constraints on our app. Our solution here is to rely on different inference libraries for each of the hardware vendors we support. OpenVINO on Intel, TensorRT on NVIDIA, DirectML by ONNX Runtime on AMD, and CoreML on Mac. That means we need a way to specify the same model to many different libraries, and that's exactly what we use ONNX for. After training models in TensorFlow or PyTorch, we convert each through ONNX to create a specification of the model architecture that can be used by each of the different inference libraries. That way, we can provide a relatively consistent result on different hardware while saving a great deal of manual work on each model. Without ONNX, we wouldn't be able to support so many new models on so many GPUs, but there are still challenges associated with any conversion. One is ambiguity in the specification. One example is that in many of our older models, we found that in some libraries, the output of the model was shifted by a pixel, and on some, the result was blurrier than on others. It turned out that those models included bilinear resize operations, and when they were converted using ONNX offset 9, I believe, the alignment of the resize was not specified, and this led to different backends implementing it differently. Some used the same rather unique input and output pixel alignment as TensorFlow 1.0's default, but others aligned the corners as would be most common elsewhere, or shifted by half a pixel, causing different results. In this case, we were able to change to a newer offset, which has more parameters for its resize operator and get more consistent quality, but ambiguity is still something we have to look for and test every time. There's also the issue that libraries aren't uniform in what they support, and even where they are, getting the best performance may mean adapting the format of the input or changing up the pre- and post-processing operations. Some degree of inconsistency is inevitable when using different sets of fused operations or intermediate accuracy, but it's not necessarily easy to quantify what's acceptable to users. And finally, performing and troubleshooting all the library-specific conversions may require getting your model to a lot of different machines just during development. So to address these, we try to avoid compatibility issues by performing test conversions before training a model. That helps avoid surprises and can give us some information about the performance. To make the most of each library's capabilities, we usually have to create a different ONNX representation for each before conversion. And this does sacrifice some of the benefits of a uniform format, but it's still faster than respecifying the network from scratch. And for quality discrepancies, using the latest ONNX offsets, explicitly specifying as many parameters as possible, and avoiding troublesome operations like bilinear resize if necessary, have been pretty useful. We still need to be sure of the results, though, so there's no good way around visually comparing the results of each conversion. But while that can be a lot of work, some tools to compute similarity scores numerically and generate side-by-side test images have been helpful. As for the hardware requirements, we've set up a CI pipeline to run conversion scripts, but while it's not very capable or quick to use yet, it's already saving a lot of time running around between computers. You may be wondering why we do so many conversions ourselves rather than using one or two different libraries like OpenGL or DirectML Everywhere, or using an existing universal wrapper like ONNX Runtime Everywhere. One reason is performance. Newly introduced hardware especially is naturally best supported by their own vendors often, and not using their interface means you can see less of a performance improvement or see it later. Using a more generic interface will also usually mean additional conversion costs or loading steps, and that can make a big difference for our apps, where users often want to compare multiple models or chain them on the same image, even though they likely don't have enough RAM to store multiple models on the GPU. Related to that is flexibility to optimize for our own models and performance needs if desired, without being obligated to write lots of model-specific code for every model, like you might with OpenGL. Getting consistent quality and speed from desktops isn't just a conversion time issue. There's also a lot of tasks in the runtime inference pipeline that we must do besides just calling a library. We need to determine which models can actually run on the user system and select the appropriate configuration, things like numerical precision, input format, and inference device. For our use, it also needs to handle running arbitrary size images through a model, despite variation in each user's and library's maximum input and output sizes, and present a uniform interface despite different setup, loading, and pre- and post-processing steps. To address compatibility and selection without having to actually test every library at runtime, which would be slow and lead to unpredictable crashes for some libraries, at the time of conversion, we also write a JSON file describing the system requirements, memory usage, input names, and other library-specific details for each variation of a model. This can be matched against system information found at runtime to determine compatibility. Selection is based on preferring the discrete GPU with the most VRAM and using the library with the most specific requirements compatible with it. This doesn't guarantee the best speed, but works well in 99% of cases. To handle arbitrary input, we split images into blocks, select an appropriate size based on VRAM, and then run the blocks through inference. This allows us to maximize throughput through batching and potentially run on multiple devices and libraries in parallel. In the future, some concerns are how to fit larger models onto consumer GPUs despite lower VRAM availability, and the perhaps related problem of how to change between different models quickly when chaining or performing comparisons. There's also continuing difficulty in ensuring new model architectures can be added and behave well across all libraries. The fact that we use more than one means it can take a lot of work and time for some newly introduced layer type or operator to be implemented in all of them and the bugs ironed out. The result of all the conversion work can be difficult to handle with hundreds of files for different models and configurations. It can be easy to miss one with the wrong permissions or a quality issue, and just moving them around takes a long time. We are hopeful, though, that the general strategy we've taken so far will be up for these challenges and enable us to frequently deliver consistent image quality improvements to get the best speed out of all kinds of desktop systems. And thank you for listening. I don't know if I can answer any questions at this point.
Thank you so much. If we could have questions in the chat, that would be great. So feel free to put questions in the Teams chat, and then Alexander, if you could answer them there. Next up, we have Pranav from NVIDIA. And again, this is a pre-recorded one, so if you're watching on Teams and the video doesn't play automatically, please hit play.
Hello everyone, and welcome to my lightning talk on Polygraphy and ONNX-GraphSurgeon. So a little bit of background on me. I work on the TensorRT team at NVIDIA, and ONNX are our primary import. So as you can imagine, we've developed quite a bit of tooling for it over the years. And this talk will cover two of those tools. The first is ONNX-GraphSurgeon, which is a Python library that lets you create and modify ONNX models. And the second is Polygraphy, which does many different things. But for the purposes of this talk, I'll cover the ONNX-related aspects of it. So we'll start with ONNX-GraphSurgeon. And at the heart of it is a Python-based intermediate representation for bipartite graphs that consist of nodes and tensors. And we'll see exactly what this means on the next slide. But you can essentially do any kind of modification on this intermediate representation using a simple Python API. And in addition to that, it provides some conveniences like constant folding, topless sorting, and dead layer removal. And I've linked the source code and examples on this slide. So here's a very small example of the IR. The basic idea here is that nodes produce and consume tensors. And so if you look in the center here, nodes have ops, names, and various different attributes. And tensors all have names, data types, and shapes. In addition to the fields shown above, inputs and outputs are also tracked. For tensors, inputs and outputs are the nodes which consume and produce them. And for nodes, they're the tensors which they take as inputs and outputs. So this makes graph traversal very easy as compared to something like ONNX helper APIs. And editing inputs and outputs lets you restructure the graph and reconnect things in the graph. And once again, everything shown here can be edited freely using the Python API or constructed from scratch manually. So in addition to the lower level APIs, there's also some higher level wrappers which make it easier to construct models. So here we'll see how to use the register API to add methods to the graph class. And they can be arbitrarily complex, and they can access the graph via a self parameter. They're totally reusable, so you can stick them in a module or submodule and use them across your project. So here's a quick example of implementing leaky ReLU. And this is using the layer API to actually define the node and tensors. And we'll see how to use this on the next slide. Once we've registered one or more ops, we can use them directly from the graph instance. And this makes creating models almost as simple as constructing TF graphs, for instance. So here we're constructing a graph with a particular input, and then we give that to leaky ReLU, which gives us an output tensor. And then we mark that as a graph output, and finally export the model to ONNX. Next, we'll dive into Polygraphy. Polygraphy is essentially a toolkit for debugging deep learning models. So it includes a Python API as well as various different command line tools. There's lots of functionality included, but for this talk I'll focus just on the ONNX tooling. And I've linked the source code and examples on this slide. Before we get to the ONNX specific tools, I just wanted to mention Polygraphy Run quickly. So this is a tool that lets you run inference with various different backends like ONNX Runtime and TensorRT, and then compare results. So here's an example of running a model.ONNX with an ONNX Runtime backend. And since there's only one backend here, it's not actually doing the comparison, but as you can see, it still runs inference. Moving on to the ONNX specific tooling, we'll begin with inspect model, which can show us a text representation of ONNX models. And the display can be configured to show things like initializers, nodes, and attributes. So here's a small example. We're doing Polygraphy inspect model, giving it model.ONNX, and we've configured it to show layers, attributes, and weights. So as you can see, it tells us the name of the model, the ONNX ops that we're using, the inputs and outputs, and you can see at the bottom all the nodes. So this is a nice alternative to tools like Netron if you're limited to the command line. Next, we'll cover tooling that can modify ONNX models on the command line. So the Surgeon Sanitize subtool lets you simplify and fold constants in the model. This is a lot like ONNX Simplifier, but it has a few key improvements. So the first is that it can preserve dynamic shapes, whereas in ONNX Simplifier you actually have to fix the shapes to use it. And even as it preserves dynamic shapes, it can still simplify shape computations where possible. It's highly fault tolerant due to partitioning. And it has special optimizations like removing conditionals, which are known at build time, and removing casts, which do nothing. Here's a quick usage example. You do Polygraphy Surgeon Sanitize, you give it the model, which is model.ONNX in our case. You give it an output path, which we're using folded.ONNX, and finally set the fold constants flag. Here's an example with an actual ONNX model. So this is a typical pattern that you might see in a PyTorch exported model. And although it looks complicated, all it's really doing is flattening the last 3 dimensions. You'll also notice that the leading dimension is dynamic, but the last 3 dimensions are all static, so this should be able to be done in a single reshape. And once we run it through Surgeon Sanitize, that's exactly what we get. The dynamic dimension is still dynamic, but the entire shape subgraph is gone. Next up is Surgeon Extract, which lets you extract subgraphs from a model. And so this is super useful for debugging. You can use inspect model or Netron to figure out the input and output tensors that you're interested in. For inputs, you also need to provide the shapes and data types. And for outputs, you just need the data types. So this is the format that the tool takes for the inputs and outputs. It's tensor name, shape, data type. Here's a quick example. And if you don't know the shapes or data types, you can use auto to indicate that these should be automatically determined by the tool. Let's do a quick example. So here's the model that we're interested in. And you can imagine that we want to extract the leaky ReLU from this model, maybe to debug it in isolation. We can see the names from the Netron view, which are identity out 0 and leaky ReLU out 1. We'll use those names and we'll fill the shapes and data types with auto so that Polygraphy will decide them for us. So here's the command. We do Polygraphy-Surgeon extract. We give it the input model, model.ONNX. We tell it the output path, which is subgraph.ONNX. And then we set the inputs, which are identity out 0, auto for shapes and data types. We give it the outputs, leaky ReLU out 1, and auto for data type. And this is what we end up with. We have a model with just the leaky ReLU, which we can now debug in isolation. Finally, we'll cover the model bisector. The tool is called debug reduce, and it's a lot like git bisect, but it works for ONNX models. The basic algorithm, assuming we start with some failing model.ONNX, is as follows. Remove some number of nodes from the model and generate a new model. If the new model fails, we repeat that process. If the new model succeeds, then we add back some number of nodes and generate another new model, and then we check if that fails. And we keep doing this until we find the smallest failing model. So I'm using fail and pass here very generally, because bisection works for any type of failure. So anything where an ONNX model is involved, bisection can be useful. That can be things from ONNX runtime accuracy bugs to issues with Netron display to even bugs in the model itself. So to better understand this, let's see it in action. So imagine we have the following ONNX model, and this is giving us an error when we run it. So we can do Polygraphy run model.ONNX, and we see this very big error message from ONNX runtime. Reducing the model to something smaller can make it a lot easier to debug. Of course, in this case, it's already pretty small to begin with, but for the sake of example. We'll start off with the interactive mode. So in this mode, debug reduce will generate models successively, and then prompt us to report whether each one passes or fails. And we'll run each of these models manually using run, and then report back what we see. The debug reduce command in this case is pretty simple. It's just Polygraphy debug reduce the input model, which is model.ONNX, and then the output path for the reduced model, which is reduced.ONNX. Here's what it actually looks like in action. I have two terminals open here. So on the left side, I'm going to run Polygraphy debug reduce, and on the right side, I'm going to check each intermediate model. So if it passes, I'll go back to the left terminal and enter P for pass. If it fails, I'll enter F and move on to the next iteration. So let's see it. So I've started debug reduce, run the model, it fails, so report failure. Run the next model, report failure again. And then we're left with the final reduced model. And here's what it looks like. So we can pretty clearly see that the reshape is invalid since the volume of the input and output dimensions does not match. That was pretty easy, but we can actually make this process easier by doing it in an automated fashion. So instead of running the command manually ourselves, we simply tell debug reduce which command to run. So here's what that looks like. We do Polygraphy debug reduce, give it the model.ONNX, we give it the output model, which is reduce.ONNX, and we give it the check command, which is exactly what we were doing manually before, essentially running the intermediate model with ONNX runtime. And the resulting model is exactly the same as what we got in interactive mode. And that concludes my talk. If you have any questions, feel free to email me at the email that I've posted on this slide. And thanks everyone for attending.
Thank you so much. Next up, we
Hello
have
everyone, and
Felix from Qualcomm. There we go. We got the audio leveled.
Hello, can you hear me? All right, great.
Yes, great.
Well, thank you very much for giving me the opportunity to walk you guys through some of the content that I put together. Is there an echo? Yeah. Better? Yeah. All right. I think we're good. We're good?
No, I can't hear you. Can you hear me?
Are we good? No? Better? I can just talk louder.
There we go.
All right, so with that, let's get going. I think that there were a number of presentations that I listened today where folks talked about different tools and how they're using ONNX and things. And that's what I'm here to talk about as well, but a little bit different. I'm not going to go into the models. I'm not going to show you any tools. I'm just going to talk to you in general what we're using ONNX for and how do we collaborate with community. Does that make sense? Okay. In case if you don't know, Qualcomm makes chips. We can't give chips away as they are. We have to give software to actually make them work. So, and the chips that we make, the SoCs that we build, and devices that we support, they range from itty-bitty tiny earbuds to the mobile phones, to the XR glasses, to automobile equipment, laptops, secure cameras, and things like that. And one of the things that hopefully you guys are going to take away is, if you come to us with a model and you're using ONNX as an interchange format, you can actually target your model and use it on all of the devices that we support and enable. So how do we do that? Very easily. First of all, if I look at what our customers and development community has to deal with, is first of all, there are a ton of different devices that are being built. Some of them, as I said, really small, really tiny footprint, itty-bitty power consumption that they can afford, to something that takes about 2 watts or less, to about 5-watt device, which is what our laptops are, plus minus, depending on how power hungry your computer is. And I know some of the folks here from competitive companies, and their SoCs are a little bit power hungrier than what we make. But nevertheless, to the automotive systems, where you have a lot of compute that's necessary with a lot of cameras and a lot of other things that consumes a lot of power, and even further than that. The next thing that we have to deal with, is the challenging architectures. Because we have to support all of these different devices, we have folks that come to us with a little bitty, itty-bitty, tiny noise cancellation algorithms that have to fit into, I don't know, 100K of memory, to folks that use devices that have to go and navigate and drive a vehicle. So they have a much more complicated models, much more data that they have to process. They have a plethora of cameras that at the same time taking images and have to figure out how to drive a car without hitting pedestrians and things like that. And the models are different, the implementations are different, requirements and timing requirements are different. Lastly, the desired features. Believe it or not, but we have customers that come to us and say, you know what, we built this model and it runs on this device, but it's not enough for us because we want to run the same device or the same model on a different configuration. And the best example I can give you is, how many folks still remember that it burned into my eyes, that Apple commercial with a guy dancing in the market, buying things with his face detection? Anybody remembers that commercial? Apple used to play it like nonstop on TV. So 4 years ago, plus minus, Apple built into the iPhones the depth sensor. And what they did with the depth sensor is they said, you know what, we integrate a camera with a depth, and using these two things, we have an unbreakable 3D face authentication. And you can use it to actually buy things using your cell phone, right? Your children won't be able to buy it. Nobody else can buy it. Only the payment system will recognize you as your face. And because they're using depth and a camera, they can make sure that it's not a picture of you and other things, and unbroken authentication path. That was 3-4 years ago in mobile phones. Next thing you know is you have the same exact algorithm, same exact capability, but now folks want to use it in a secure cameras, where you walk up to your home, you already have probably like a smart doorknob or a ring, one of those things. They recognize you, they look at you, they use exactly the same model, exactly the same thing. Authenticate it's you, open the door for you. You can get in to your house, okay? Move the time to today's dates. There are plethora of cameras these days inside automobile, right? And outside. So what they can do is the automotive guys now come to us and say, we want to use exactly the same algorithm, exactly the same technology. All these things that you already certified for payments and certified for processing and unlocking your phones, now we want to have it in a car. So when you walk up to your car, the car recognizes you, opens the door, you sit inside your vehicle, they'll see that you're licensed and authorized driver, using exactly the same algorithm. Nothing changed, nothing modified, same exact model, same exact train material and everything else. Now they look at you, they recognize that you is you, you're an authorized driver, and in addition to that, sometimes they even look at you, make sure you're not distracted or drunk or things like that, and then they'll let you start the car and drive off the vehicle. So scalability, So that's kind of the last challenge that we have to deal with. Thank you. So the way we've done it at Qualcomm is, and I know there are folks that talked about how you can process machine algorithms on the CPUs. Good for you. And I've heard other folks talked about GPU and how fast this GPU is and how awesome it is that they can get better processing. The way we'll look at it is, if I take a model, I don't know, Inception v3, maybe something like that, and I can run on a CPU on a decent frame, so the decent resolution, I can probably get about, I don't know, 5 frames per second, inferences a second on a good day, right? So you give me a picture, 5 times a second, I can look at the picture and tell you there's a dog in that picture, okay? If I take this exact algorithm and its model, it's got converted to ONNX-RT, to ONNX, and then you're running on a CPU. I take this model, I removed it and said, I want to run on a GPU. Much faster. How much faster? I might get about 30, 40 inferences a second, which is borderline useful because now, instead of processing a picture at the time, I can do inferencing on a live video stream. Maybe it's not 60 frames a second at a good camera, but 30 frames a second I can probably deal with. Now, if I take this exact algorithm and move it off to the AI accelerators that we have in Qualcomm devices, and from other vendors, they have their own, I can probably get, I'm talking about on a range of 1,000 inferences a second. So not only I freed up CPU to do something useful, not only I let my GPU to deal with dealing with displays and resolutions and doing the GPU kind of stuff, now I'm using AI on this specific for-purpose built AI accelerator that barely consumes any power and is much, much faster. And the way we scale is we take this exact architecture and we make it multi-core, if you're talking about like automotive kind of equipment. And if you want to go into the cloud and do inferencing at the edge, we have devices where we stack up a whole bunch of these AI accelerators, parallelize them, and then we can do kind of cloud-level workloads on that. And that's how we scale our hardware. But scaling hardware is not good enough. To deal with that, you have to actually scale software as well. And these are just few things that I had pictures in my slide deck. I was asked to actually put bullets. So bear with me. First of all, we have customers that come to us from all over the place. And the benefit of them using ONNX as an interchange format is because they can go from whatever training framework they use to ONNX, and then we can have it translated and compiled directly to execute on our hardware. And when I say on the hardware, I mean that we can take this ONNX model and hook up a backend for it and conversion to the CPU, to the GPU, or to our AI accelerators. You don't have to change the model. We will handle all the translations and all of the compilations behind the back. Well, I already covered the second bullet point, the direct conversions. And that helps them to scale. It helps them to scale across the capabilities of device. The same ONNX model can run on a small device, more powerful device, more capable device. And it also helps to scale across the verticals. Like I said, you build things for mobile phone, and then you can use the same model on a smart camera, and then you can use the same model in a cloud. Now, to us, and that's something that we talked about during the lunch, it saves a lot of time to Qualcomm. Because instead of me having a paddle-paddle converter and accelerators and be able to accelerate that, and all other frameworks from other regions and geographies, I just have an ONNX converter that takes ONNX interchange format and compiles it into a binary that executes on the device. That's it. I just need to have one, rather than dealing with all these other frameworks one at a time. And lastly, there are folks that come to Qualcomm from kind of two different paths. Some of them come to us and they said, here's the model. I want to get it to the ONNX, use it as an interchange format, and then use Qualcomm software stack to accelerate it on device. A lot of those are folks that build for-purpose devices. They know what they're looking for. They know exactly how they want to partition their models and how to set up system parameters and CPU power and everything else. Then we have a second type of customers that come to us and say, you know what? I just have a model, and I want to run it on as many devices as possible. I don't want to go and worry about specific Qualcomm hardware. I don't want to worry about other things. So to them, if they use ONNX-RT, then that will kind of protect them and allow them for this portability. So one of the things we're doing right now is we're working with Microsoft on ONNX-RT executional provider for our AI accelerator. Again, not CPU, not GPU, but specific AI accelerators that the ONNX-RT will directly delegate to. Next slide. Again, to Qualcomm, the way we solve it is we put together a unified software stack that allows you to scale across the verticals and across the tiers and complexity of these devices. And how do we do that? Very simple. First of all, we have to support, and I don't know how about other vendors that talked about before, a plethora of operating systems. I don't know if you guys recognize some of them. Anybody has their preferred operating system for devices? So if it's a mobile device, it's obviously Android. If it's an automotive device, things are a little bit trickier, like QONNX and others. So depending on the type of device you're using, we have to support that operating system, including even Windows. So the folks that haven't used it, I have right there. For the last 2 years, I used Windows on ARM device from Microsoft. Extremely happy. Lasts me a day or more. Dealing with system interfaces and drivers and support, kind of hiding all the underlying hardware and OS details from you. And then what we've done at the top is we have a unified software library that Qualcomm put together, Qualcomm AI Engine Direct. And the reason we call it AI Engine and not CPU or GPU or a Hexagon AI accelerator is because when you come to us with an ONNX model, we will take care of routing it to one of those things. We can dynamically change it. If you are playing a game, we don't want your AI algorithm to use GPU. We want to offload it to something else. If you're not playing the game, if you're using your phone and just talking, well, gee, when you're talking on the phone, what's GPU doing? Usually it's off, display's off. It detects that it's next to the ear and turns off display. So we can take your AI model and push it to the GPU since it's sitting there doing nothing. And then on top of it, again, as I said, we take ONNX Runtime and we're providing a delegation to it. That way, we can take your model and get it the best performance that you guys deserve when you're using Qualcomm hardware. Frameworks we have to support, obviously. That's kind of how our software stack looks like. And then the rest of the tools, I don't have time, but I would love for you guys to come to me and tell me, what do you use today for tools? We have profilers, we have compilers, we have analyzers, we have enablement for the NAS tools, network architecture search tools. If you want to build your model from scratch, go for it. If you want to go and quantize it, we have a ton of tools that helps you to quantize. I didn't know the experience of the audience, and I don't want to spend your time talking about all the intricacies of INT4 support versus INT8 versus FP16 or INT16 and how much data throughput and power it saves. But if you would like to, I'll be more than happy to send me a note, and I'll be more than happy to take your questions and answer those questions about the tools or the underlying technologies. With that, again, hopefully some of the things I explained and how we're looking at the software stack that we put together will kind of answer some of the questions from the audience. It's like, okay, so how do we actually deal with scalability and using ONNX to give customers ability to kind of write their algorithm once, convert it to the ONNX interchange format, and then run it everywhere. Whatever you're using, camera algorithms or building something for connectivity for either camera or XR or compute. Requirements are different. Things that people do on XR device that is battery operated, has 2 displays in front of your eyes, and has to deal with a lot of concurrencies, very, very different than things that you're doing in a smart camera or smart speaker. Use cases, again, the smart speaker probably has a ton of models, but they're all audio-based, translation, transcription, things like that, versus XR glasses where a lot of it is imaging and be able to deal with computer vision and things like that. And that is my last slide. Thank you very much for giving me a chance to talk to you guys. If you have any questions, feel free to find me in the hallway, and I'll be more than happy to answer them. All right?
Thank you so much. Next up, we have Tung from IBM, and he'll be presenting virtually live. Tung, we're not able to hear you if you're speaking.
Hello?
Now
Can
we
you
hear
hear me?
you. Thank you.
Okay, thank you. Wonderful. So we start now, or wait a few minutes?
Cassie, can you tell him to start?
We lost you.
No, he's asking if he should start.
Oh, yeah, go ahead, please.
Okay, thank you. So good morning, good afternoon, good evening, everyone. So my name is Tung Le from IBM Research. So today I'm going to talk about our update on ONNX MLIR, so which is a compiler for ONNX model. So it's a sub-project inside ONNX. So you can see its link here on the screen. So let's start with what is the ONNX MLIR. So it's a compiler to compile an ONNX model to an optimized binary for different architecture or machine. So to obtain an optimized binary, we use MLIR and LLVM. So why LLVM is well known for low-level optimization and code generation. So MLIR is an emerging infrastructure for high-level optimization and code transformation. So in that sense, the compiler is totally based on open source infrastructure. So we have been developing the project since 2019. So it's quite young, but an active project. So on average, we have about 10 to 20 commits per week over the last year. And the number of unique visits during the first 2 weeks of June was quite large. And I think half of them on the repository. So the project has attracted interest of some big companies such as IBM, Microsoft, ARM, Facebook, and others. Oh, sorry. So we have several goals when developing ONNX compiler. So firstly, we would like to have to provide a reference ONNX dialect in MLIR, so which is an interface to bring ONNX to the MLIR world. So as a compiler, so we expect that it is convenient to write the optimization, so not only for CPU, but also for new custom accelerator from high level to low level optimization. So it should be easy to deploy. So for end user, we support 4 main languages such as Python, C, C++, and Java. So for developers, it's easy to integrate with other MLIR-based compiler. Finally, we expect that the compiler will be thoroughly tested. So not only by unit tests, but also the whole model test on different architecture, different operating system, and programming language. So this page shows how the compiler has been tested and deployed in practice. So on the front page of the GitHub, so we have a live report for different environments. So to see whether the current commit is a pass or not. So we also report the status of the ONNX model zoo. So so far our compiler can compile and run more than 100 models. So the compiler has been deployed in IBM Watson machine learning for ZOS. So it has been used for online scoring service. And BentoML, an open source model serving framework is using ONNX-mlir as one of the inference engines. So in this year, so we newly introduced a framework for supporting custom accelerator. So these frameworks allow us to quickly add a new accelerator to the compiler. So we can choose which ONNX operators will be uploaded to accelerator. And each accelerator can have a special optimization specific to that accelerator. So it means that in our framework, accelerators are pluggable, and it can be turned on and turned off easily. So as a proof of concept, we now support IBM on-chip AI accelerator, which has been introduced in IBM Z16, announced recently. Let's look at a little bit more on how optimization are deployed in ONNX-mlir. So from top to bottom, so an ONNX model is gradually lowered into intermediate representation, and finally a binary is produced. So at each intermediate representation, we have multiple dialects for CPU and accelerator. So some dialects are built-in dialects from MLIR, some newly introduced in ONNX-mlir for CPU and accelerator. So at the high level, we have high-level optimization, such as shape inference or graph-level optimization. And at other level, we have optimization for CPU operation and accelerator operation. So some optimization can be applied at multiple levels, such as constant folding or canonicalization. And finally, we would like to show how accelerators help speed up the inference for a practical model that is credit card fraud detection. This model is used for real-time detection of fraudulent transactions. So we did experiment on IBM Z16 compared to running on the CPU as a baseline. So using accelerator is about 11 times faster. And we cannot disclose more in detail, so because it is related to an IBM product. So, but what we would like to show here is accelerator framework in the compiler works indeed in practice. So in summary, so we believe that ONNX MLIR compiler is convenient to do the optimization and to support a new accelerator. So as an open source project, so we would like to have a contribution from a community to grow it. So in the near future, we continue to optimize the important operator like convolution, pooling, reduction, etc. And well, we will support the ONNX machine learning operator. So now we are focusing on a deep learning operator, but we still have a lot of work for ONNX machine learning operator. Finally, we also want to support the other accelerator, such as GPU. And finally, we in this thank all contributor who have been contributing or will contribute to ONNX MLIR. Thank you.
Thank you. Thank you so much. Next up, we have Preferred Networks. They are presenting virtually live, so we'll get them connected. Be sure to take control and unmute yourself.
Hello?
Can you say something one more time? I think you're a little quiet. We might need to turn it up on our end.
Okay, hello, can you hear me?
We can hear you.
Thank you. So I will begin my presentation. Hello, everyone. I'm Sujan Xu from Preferred Networks, and today I'm going to talk about PFVM, a neural network compiler that uses ONNX as its intermediate representation. I'd like to first introduce briefly about our company, Preferred Networks. Preferred Networks is a company located in Tokyo, Japan. So it's 7:15 in the morning here, and we have various projects, and we are solving real-world problems by deep learning, such as material discovery, medical image analysis, character design, and many other projects. We also have some open source projects known as QPy, which is a NumPy compatible tensor library accelerated by CUDA. And we also have a black box optimization tool, Optuna, and we used to develop Chainer, a defined by Run-styled framework for writing neural networks. And we have our own supercomputer for deep learning code MN3, which is known as the most energy efficient supercomputer in the world. And I am a member of compiler team, and I'm in charge of developing PFVM. So today's topic is I'd like to share a use case of ONNX for model optimization. I think the most popular ONNX use case is for model deployment. We export ONNX from Python code and we deploy the model to edge computing architectures using ONNX Runtime or some other libraries. But I'd like to focus on model optimization today. And secondly, I'd like to share our motivation to have a solid shape inference functions. So PFVM is PFN's preferred networks, we say PFNs, PFN's in-house neural network compiler and runtime. PFVM works as both compiler and runtime. So PFVM takes exported ONNX as input and optimizes it and executes the model with specified backends using third-party APIs. However, unlike other inference engines, PFVM can be also used for training models. In such case, PFVM compiler extends the input ONNX and appends the gradient nodes for training. This is how PFVM works. So given the input ONNX graph, if the model is for training, then we generate backward paths. And after that, we optimize models. So during optimization, we have various kind of optimizing paths, and some of them are going to be explained later today. And during optimization, we extend ONNX by some custom operators. For example, since ONNX does not contain device information, we add host to device operator and device to host operator to optimize device changes and memory. And after optimization, we schedule the computation graph and get a sequence of operators. And after that, we execute each operators using LibTorch API or some accelerators APIs. And we have several reasons to use ONNX as intermediate representation of PFVM. First, ONNX is stable and well documented. It does not change very often, so it is stable, yeah. And secondly, focused on interface and doesn't do too much. And ONNX shape inference is very useful. We don't have to write shape inference function by ourselves. And moreover, ONNX has useful test cases in its repository, and we use them for many test code. And let's see how shape inference is important in model optimization. And we have several optimization, but I'm going to introduce 3 today. And the first case is element-wise fusion. Yes, let's take a look at this ONNX model. So we have 2 inputs, A and B, and we first reduce A and get a scatter and other constant, and then we subtract and multiply something and get the output. When we execute this computational graph on CUDA, the CUDA profile will look like this. So we have reduced max kernel, add kernel, subkernel, mul kernel, and before each kernel, we have overhead known as the CUDA kernel launch, and it is important to reduce this kernel launch overhead for faster computation. And if we can fuse these element-wise operators into a single fusion group operator, then the kernel launch is only twice, and the computation time will be reduced. So basically, we want to fuse element-wise operator every time, but can we always fuse adjacent element-wise operators? The answer to this question is no, and we must check whether they can be broadcastable or not before creating a fusion group. So in the left case, since all of these values have shape n, they can be fused together. But in the right case, where A has shape n and B has shape m, then we cannot fuse these operators together because we don't know if m is equal to we don't know if n is equal to m or not. So please see this case. So in this case, if shape inference is failed and we get unknown shape, then this is very troublesome case. So in this case, we have a single input x, which have shape A times B, and we reshape it to one-dimensional tensor. So unknown 0 and unknown 1 is both A times B. So they have the same shape, but current ONNX shape inference cannot infer that unknown 0 is equal to unknown 1. So in compile time, we don't know that these unknown values actually have the same shape. So we lose fusion opportunities in this case. So shape inference is important here. And the second case is graph simplification. I think many inference engine do the similar optimization here. So again, we reshape this value to one-dimensional shape. So in this case, we know that unknown 0 is equal to A, but again, current ONNX shape inference cannot infer unknown 0 equal to A, so we don't know that A is equal to unknown 0 in compile time. In this case, we can, so if we can infer that A is unknown 0, then the reshape is just the identity, and we can remove the operator, and we can do the element-wise fusion. But we cannot do this right now. And you may have a question like, do model contain so many unnecessary operators, or do we really have to do this kind of optimizations? And the answer to this question is, well, I think models does not contain so many unnecessary operators if the model is written by human, but models may contain a lot of unnecessary operators if it is generated by programs like backward pass generation or neural network, neural architecture search. And I'd like to show an example of how these optimizations are important in an example. Let me proceed the slide. Oh, as the appendix is not included. Oh, okay, then I just skip this part. Well, what I wanted to explain was, so if we generate backward path for a specific node, usually the backward path is a little bit complicated. So, well, I'm going to just skip it. And the third case is automatic checkpointing. And some of you may have heard of checkpointing before, but I'm going to explain it from the beginning. The checkpointing is a technique to reduce memory usage when executing a model. So let's see the left computational graph. In this computational graph, from two inputs, X and Y, we compute Z. And however, when computing this computational graph, the memory usage is not very good. I mean, when you compute node 5, you have to remember the output of 1, output of 2, output of 3, output of 4 on memory, and the memory usage is costly. However, you can modify the computational graph to this example, examples. But these computational graphs are different, but computes exactly the same output, because the node dependency is completely the same. So, but all of these computational graphs have different latency, which is execution time, and different memory usage. So PFVM automatically transforms the input ONNX graph so that the latency is increased a little bit, but the memory is reduced a lot. PFVM can do such optimizations. And it is very important to need to know tensor sizes to estimate memory usage. And it's relatively simple when models are static. So where we don't have dynamic dimensions there. But even when models have dynamic access, we can do automatic checkpointing because users can estimate them in compile time. Like number of nodes is 1 million in some graph neural networks or something like that. However, unknown dimensions are not welcomed in automatic checkpointing because well, we don't, the estimation won't work. We don't know if the unknown dimension is just 1 or just 2 or 1 million or something. So this is the summary slide, why shape inference is important. So once we get unknown dimensions, we will have many unknown dimensions after that. So usually in most shape inference, if the input tensor has unknown dimensions, then the output tensor also have unknown dimensions. And we lose many opportunities of optimization if shapes are unknown. As we see, where we cannot do element-wise fusion, we cannot do graph simplification, we cannot do automatic checkpointing. And let me say my ideas for current ONNX shape inference. So as you may already know, ONNX shape inference has been improved a lot recently, and symbolic inference was introduced from 1.10. Symbolic inference is a shape inference scheme using data propagation. So for example, in the right case, we can infer the output shape of constant of shape as A times B from the input tensor of shape 2, because the A and B are propagated globally from the top shape information. And this is really nice. And for static case, I think current ONNX shape inference already works quite nicely. And we can run the shape inference in most of the time for major workloads. But for dynamic case, I think we want more support. So this ONNX graph is an example that I showed a little bit earlier. So in this case, we want to estimate the output the shape of reshape to be A, but currently it is unknown 0. And well, I think we have to implement more shape inference functions for dynamic case. And well, I have a question like this. Do we need to support case like concat of two tensors of size m and n? Well, I think this question is a little bit controversial, and I'd like to hear some use case if you think this shape inference is important for your workload. This is the last slide. So this slide is a little bit not so much related closely to ONNX, but this slide is for optimizations. So we have our PFVM's own supercomputer called MN Core, and MN Core only accepts static model. So the models where all of the tensors have a static shape, and model does not have dynamic branching. So MN Core does not accept models that contain if or loop. But since the models are static, MN Core can do many optimizations. MN Core is a very large-scale fast SIMD machine, and its scheduling is really challenging. And where we use the static information to do a very sophisticated optimizations for scheduling. Yeah, the interesting thing is, since MN Core is model static, MN Core programs know exact computation time or memory usage or memory address of everything before running the model, so at compile time. And PFVM is integrated in MN Core compiler and do some of simplifications and shape inference. So what I want to say is, if the shapes are known, we can do shape inference, we can do many optimizations. the shift inference is very important in every optimizations. So thank you very much. If you have any questions, please ask it on chat or please reach out to me. Thank you.
Thank you so much. Next up, we have Huawei. They are doing a virtual pre-recorded. So again, if you're on Teams, you might have to hit play.
Hello everyone, my name is Xiyuan Wang from Huawei. Now I'd like to share the topic to you. It is called Bring the Power of ONNX to Spark as it never happened before. This slide is prepared by Yikun, Zhipeng, and me. Okay, let's start. This page shows the simplest workflow of inference flow of data and AI pipeline. In general, the user uses the Spark as data processing platform and uses the ONNX Runtime as inference platform. The well-defined data frame inference interface is very friendly to data engineer, and the data engineer can easily to load data and complete the feature engineering. They are very proficient in data processing as the de facto standard of the big data platform. Spark can help users easily and conveniently use a simple interface to divide huge data into each executor. Especially in recent years, Spark has enabled Pandas on Spark API since version 3.2, which is also very convenient for users. At present, various AI frameworks such as TensorFlow, PyTorch, Manspur, and so on has their own implementations for developers who use AI framework. They are often proficient in parameters tuning of AI frameworks and the internal principle of frameworks. There are some gaps or friction points between the two because data engineers often do not understand the framework very deeply and they do not know the internal of various frameworks. And the same as AI engineers, they don't know the deeply about the big data framework. Therefore, the Spark community has also initiated a discussion on Spark improvement proposal. It is called SPIP, hoping to head the complex process of each framework by providing a simple API, and to make the process of Spark and AI inference smoother. The goal of this SPIP is to simplify the deployment of DL models to Spark inference, enable integration with third-party DL frameworks, and the target persons are data engineers who need to deploy DL models on Spark, or the developers who need to deploy DL models on Spark. You can also search the JIRA to learn more. This SPIP is still under discussion. If you are interested, you can join the discussion as well. This is a simple example to show how the developer should complete the inference after DL on Spark enabled in the future. We can say that the only thing the user needs to do is to import the corresponding framework extension and model URL. Then all the complexity, including type processing, conversion, and framework initialization, are hidden in model UDF. What each framework needs to do is to implement the corresponding implementation according to the actual situation of the framework. Then see the right picture. The Spark will help you to execute the ONNX inference in Spark executor, and Spark will help gather the final result. In this way, users can easily complete ONNX inference on big data. ONNX Runtime is an inference platform to optimize and accelerate machine learning inferencing, especially by providing a well-defined middle layer. It builds a bridge between the underlying AI acceleration hardwares and model inference with ONNX format. Huawei has its own AI processor called Ascend. So if we want to complete the Spark and ONNX pipeline on the Ascend platform, we should introduce Ascend support in ONNX Runtime first. First of all, I'd like to introduce the basic concept of Ascend. Ascend is the name of NPU AI processors from Huawei. Around it, Huawei has built the Ascend AI ecosystem. Let's take a look at the graph here. The gray rectangles here represent different Ascend processors models. Ascend 310 only supports AI inference, and both 710 and 910 support train and inference as well. Based on the processors, Huawei built a series AI-related hardwares, which shown in the blue rectangle. They are called Atlas. Here, I'd like to say more about Atlas 300. It's a kind of PCI card and used widely on data or AI process servers. Our develop and task work is based on it as well in ONNX. Then, based on the hardware, Ascend ecosystem also provides a software layer called CAN. It is the yellow rectangles in the picture. CAN provides APIs to help developers quickly build AI applications and service based on the Ascend platform. Frankly speaking, it's similar with CUDA in NVIDIA ecosystem. For software, CAN is the main point that both developer and AI framework should know. Let's focus on CAN here. This is the CAN technical stack view in Ascend ecosystem. Last year, my colleague Zhipeng has shared the CAN stack already in the ONNX meetup, where it was based on CAN 3.0 version, which is out of date. This picture here shows the newest version called CAN 5.0. As you can see here, there are multiple layers in CAN. It contains service layer, compilation layer, execution layer, and the base layer. For example, service layer provides operator library, optimization engine, and a framework adapter. In general, developers do not need to know them. You may only focus on Ascend computing language. It's called ACL. It's the API's part to help you control Ascend hardware's via CAN. Currently, if a user wants to run ONNX model on Ascend hardware, he should first use the model translation tool provided by CAN to translate the model from ONNX to Ascend. The flow is a little complex, and the translated model may lose some precision, and the performance may poor. Even in some cases, the model cannot work correctly. To solve the problem, a better way is to find a solution that ONNX model can work on Ascend directly. So in ONNX Runtime, we'd like to add CAN as a new execution provider. Once it is done, users can use ONNX model on assigned hardware via ONNX Runtime directly. Of course, we'll add the related CI as well. For example, we can donate VM resources which contains assigned hardware to the community. The orange line below is our roadmap. First, we'll push the basic code to upstream. The end-to-end flow will be done, and the REST-NIght model should work correctly. At the end of this year, we'll finish all the ONNX operators support and make sure all the models in ONNX Model Zoo works well on Ascend. In the next year, we'll focus on optimizing work, for example, like performance improvement and so on. Now the POC code is almost done. Use the POC code, you can now run some basic operation correctly on Ascend using ONNX Runtime, for example, the add operation. If you are interested, please leave us the message. We can discuss more in the future. Maybe we can provide Ascend resources for you to test as well. Okay, that's all of our topic. Thanks for watching. Bye-bye.
Thank you so much. That was our last talk of the day. Lots of good content here. So next up, we're going to be doing the roundtables. So I'll say goodbye to the people virtually. Thank you for hanging out as well. The next part will actually just be for our in-person attendees. So for the roundtable discussions, how many have done like an open spaces or something like that at a conference? Like raise a hand. Has anybody done that? Okay. So basically the idea is that we asked you all to submit topics that you were interested in talking about or talking with other people about or learning more about or sharing your knowledge, that type of thing. And so we have 6 different topics. This wall is going to open up here, and we have round tables over there, and we have big notepads for you to write on, and we have topics listed on them. There's the 6 topics that we selected from what you provided, and there's also 3 empty ones for somebody if they want to add new ones. Go to a round table that looks interesting to you, and that's kind of the topic of the conversation. If the conversation kind of goes off topic, that's fine as well. We're also going to have the ONNX Runtime team around. We'll be joining in on the conversations, including Manesh will be at our ONNX for mobile and edge. He works on that for ONNX Runtime. We also have an ONNX Runtime specific table. We'll have ONNX model deployment and ML quantization, training and ops and conversions and operators as well. So this will open up any minute. Open sesame. It didn't work. And then we'll do that. Then also after that, we will be having the happy hour set up around 4:15. So pretty shortly the happy hour will be set up if you want to keep the conversation up and grab a beverage and go back there. Otherwise you can hang out in the gallery space. We'll have food and beer and wine and soda and such. And then lastly, oh sorry, no, I have 2 more things. If you could fill out the other side of your survey, so the survey had 2 sides. One side was for the first half of the day, the other side was for the second half of the day. Let us know what content you really liked, what you didn't like, what you would like to see differently, if we host it again, that type of thing. We really appreciate your feedback. And then your name tags, to facilitate conversation, both at the roundtables and at the happy hour. We have some Sharpies back at the table. If you could add your company onto your name tag so people can kind of see. I think a lot of people already did, but if you didn't, if you could get that added, that would be great. So thank you so much. Wall still isn't opening, but it should. If the wall doesn't open, we can also go through the door. But it's like more dramatic door opening, you know? Yeah, can you open it now? Yeah? It opens up and there's another room like this with different round tables. I just thought it'd be easier